Good afternoon, ma'am.
Good afternoon, ma'am.
Good afternoon, all the participants. Ma'am, still participants are slowly joining. Meanwhile, I'll introduce and we will start the session, ma'am.
Sure, ma'am, sure.
Dear participants, it is indeed a pleasure to welcome back Dr. Ashwini Kodipalli for the second session of today's first session, but is the second session continuation to the previous session, which was taken on CNN on 6th January 2026. Dr. Ashwini Kodipalli is a research associate at the Indian Institute of Science, IISc Bangalore, having 14 years of academic and research experience in artificial intelligence, deep learning, medical image analysis, biomedical signal processing, and intelligent healthcare systems. In the earlier session, she provided valuable insights into deep learning and CNN architectures for medical image analysis. Which was highly appreciated by all the participants for its clarity and practical relevance. Building on the strong foundation, in this session, Dr. Ashwini will be addressing another important and emerging area of healthcare AI, explainable AI for remote monitoring and wearable healthcare devices using IoT. Her expertise in AI-driven healthcare solutions, combined with her interdisciplinary research experience, makes this topic especially relevant in today's context of smart, connected, and patient-centric healthcare systems. We are delighted to have her once again with us. Look forward to gain deeper insights into how explainable AI and emerging technologies can enhance trust, transparency, and effectiveness in remote healthcare monitoring. Now I invite Dr. Ashwini Kodipalli to kindly take over the session. Ma'am, please start the session.
Thank you, Sujata, ma'am. Good afternoon. Good afternoon, everybody. I once again thank the management of Srinidhi College for having me. Today we will be, ma'am, is my screen visible? Are the slides visible?
Yes, ma'am.
Yeah, okay. So this is what will be the point of discussion today. Let me minimize. Yeah. So it is AI for remote monitoring and wearable healthcare devices. More specifically, I'll be focusing on explainable AI concepts. In the previous session on 6th, we have seen a CNN architecture. Since all the participants here are research scholars and faculties, so one suggestion to all of you. Nowadays, whenever we are working on a CNN, if you just propose a new CNN architecture by increasing the number of layers, or if you come out with an hybrid CNN model, going up to a good journal will not be possible, because all that around 5-6 years back, it would have been a good research. But now the focus is more towards an explainable AI. So today, since the previous session we have seen on CNN, so I request everyone to get into explainable AI also, so that it is a perfect combination. So you can come out with a new architecture, and then you can apply an explainable AI techniques, and then make as one objective for your research. So for that, this is the main motive behind going for an explainable AI. And why is that we are choosing an remote monitoring and wearable devices is, nowadays we can see that there are so many smart healthcare devices which are monitoring our parameters by wearing it to our body. Probably it can be a smartwatch, or it can be an devices which can be connected to the body, and those are going to take our parameters. So once we take those parameters, what will be the next step? We are getting a live data and or a real-time data. Once we get the data, we have to apply any of the algorithms. It can be a simple machine learning algorithm, or it can be a deep learning algorithms. So with those deep learning algorithms, we are going to get the result. So what next after the result? Can we trust those results? Are the results really reliable one? Can we use those results for an ethical use? All these are the questions, right? So for that, we need an answer. That answer is an explainable AI. That will be the point of discussion for today's session. So, one second. Ma'am, I'm not able to take the slides to the next one. Can you make me as a co-host?
Yes, ma'am.
Yeah. Okay. Uh, so these are the discussion or the contents for today's session. We will first see what is the need for an XCI, what exactly is an explanation in XCI, and what are the different techniques that are available. So there are many different techniques, but we will be focusing on these three techniques in today's session. So let's get started with what is the need for an XCI. So before the invention of these topic, so how conventionally deep learning or any of the computational algorithm works, we have an input data. That input data can be an images, or it can be an audio file, video file, or it can be a tabulated data. When I say tabulated data, the data here is taken in the form of a CSV file or the data taken in an Excel file. That's what I mean to say tabulated data. Or you may be working on an text. So you take an input data. That input data is passed to a neural network or any learning models. When I say any learning models, it can be even machine learning also. Then what is that we get? We get an output, or the model is going to predict. So what model has predicted, how well the model has predicted, how will we verify? We use any of the metrics. It can be an accuracy, precision, recall, F1 score. It can be any of those metrics. Now, we got 98% accuracy. Say, for example, for some model, we got 98% accuracy. Now, we, ask some questions to yourself. What are those questions? Can I really believe this 98%? On what basis the model has given this 98%? At least in tabulated data, that is in CSV file or in an Excel file, you will have the feature names. At least in those, you can see those feature names. But when it comes to images, on what basis the model has given this 98% accuracy? Do we have an answer for this? Definitely no, right? So, despite their efficiency in terms of very good performance, often we call the neural network or computational models as a black box system. Why? Although it gives a very good accuracy, but they are not easily understandable by humans. Therefore, these neural networks or learning models they lack in transparency. Because they lack in transparency, they raise certain concerns such as trust. Can I really trust this 98% accuracy? Accountability is just because I got 98% accuracy, can I treat the patient as, suppose a person input image is characterized as a malignancy. So can I start giving a treatment for malignancy? We cannot do that, right? If something goes wrong, who is accountable for this? Fairness, will the model perform correctly for all the samples? Can I use it for an ethical use? So when we have a questions of these kind, we don't have an answer for any of these. Therefore, there is a need now for a system. What kind of a system? Now, pass an input to an explainable AI methods. Now, what explainable AI methods does, it is going to give us the output. That is, it is going to give us the accuracy, which is 98%. Now, when I ask the question, why did you give this 98%? What exactly you have looked into and into this image? It is going to give us the visual reasoning. So it says that this is the input that you have passed. For this input, this is the region that I have looked. Okay, let me take the pen. Yeah, this is the region that I have looked. So I think there is some abnormality here. Based on this, I have, given this 98%. When I passed this image, this is where I have looked into for my prediction. So is it not the doctors also say in a similar way? When we first doctors say, go get the X-ray test done. With an X-ray, the doctor look into that image and say that, look into this region, there is a disease here or there is a problem here. So how doctors are going to explain these explainable AI methods also will give us that explanation. So now what exactly has happened? Previously, now there is a shift. Shift from what? From prediction only. This was just a prediction. Maybe the model has predicted a particular image as pneumonia, or the model has predicted it as normal without pneumonia. This prediction only to now what has happened? Prediction with explanation. So this has led to an immense shift in trusting these deep learning models. This is very much essential for building a human trust so that you can now deploy these algorithms or deploy the model that you have built for a real-time applications. These XCI is especially useful for high-stake applications, which are considered as high-stake applications. It can be any medical diagnosis, or it can be an autonomous driving, it can be a fraud detection, or any judicial decision making, where any incorrect predictions will have an immense serious consequences. So there it is just not getting an output, but we are also expecting us to have an explanation-based prediction. So I hope you are now understanding. Earlier, the need was let deep learning perform the task, which human otherwise is taking too much of time. So machines will give the results faster. That was the need once upon a time. But now the need is, okay, anyhow, machine is giving us the good result. Let me ask the question on what basis you have given this. That led to a development of an XCI. So the full form of XCI is explainable AI. So now what exactly is that word explanation here? What all that XCI can answer to us is, let's take an example. Now we have an data set. Let us take an ovarian data set, and we have taken a simple CSV file here, and it is a multi-class classification which has benign border case and malignancy. Now we have built an deep learning model. Since it's a simple CSV file, we have built an ANN model. Now, I'm passing the first sample, and the model is well trained. Now, during a testing, you have passed the first sample. Now, for the first sample, the model has predicted it as benign. Okay, now you are passing the second sample. For the second sample, the model is predicting it as malignancy. Now, the first question is, why did the model classified S1 and S2 as benign and malignant? Why? On what basis? This is the first question. And second, here there are many features, right? A data set will have many features. Which are the features which are most influential in taking the decision? So this is the second question. And the third one is, can I do certain changes to these feature values so that the output is going to have an impact? How would the output to change if certain input were modified? And the next question, can we really depend on the model's decision? Now, for a particular sample, it has classified it as malignant. Can I really depend on model's decision? So these are the questions. Now, what is the topic here? What is an explanation in AI? So answering all of these questions is actually an explanation in AI. And this is exactly the role of XCI. And by answering these questions, is it not we get a kind of a trust? Now go back and then relate it to a real world. When we go with some problem to an hospital, first initially what a doctor will tell? Doctor will tell that go get the following tests done. Then after a day or two, we get all the reports. With that reports, we'll go back to the doctor, and doctor will look into all of these reports and say that the patient is being diagnosed with so and so problem. Then immediately, what is that we do? Is it not we ask a question to the doctor? Doctor, on what basis you are saying that I have been diagnosed with this problem? Why you're saying that I have this particular problem? Which are the parameters which have really contributed for my problem? So is it not you ask these questions? And is it not a doctor will look into all of the reports and say that, look, your this particular parameter is very high. In the blood test, this particular parameter is very high. In the scanned report, it says that the tumor size is so and so. So by answering those your questions, is it not you build a kind of a trust that yes, you are being convinced that I have really this particular problem. So this is what now the need is. This is what explainable or XEI does. I think the context is set clear to you. Now, with this, let's get into the most important. If XCI really does all these things, then which are the algorithms which are going to do these things? So the entire algorithms are characterized into 4 different categories. One is called permutation-based method, or the first basic initial techniques that was a technique that was invented was permutation-based method. What is permutation-based method? How does this particular method works? Take an input, shuffle the entire input, and then see how the prediction is going to change. So this is how we will look into one of the example. So this is what is a permutation-based method. Under this, the following are the algorithms that we have. We have PCI, then we have occlusion, then we have SHAP. So in today's session, we will take one of the example under permutation-based. We look into SHAP. Second technique, what we have is a post hoc and model agnostic. What is a post hoc is whatever the model that you have built, once the model is trained, then you are asking the model certain questions. So not before training, after once the model is trained, you are asking certain questions to the model. That is the meaning of a post hoc. These are the methods which generate the explanation only after the training is completed. Second, what is model agnostic? Model agnostic are those methods, now under this, the example is a line. Line is one powerful AI technique or explainable AI technique that works on any algorithm that you apply. First, you have built a machine learning algorithm. Machine learning algorithm has given you the prediction. Now you use a line to explain. So line give the explanation. You take ANN model, you take CNN model, you take any algorithm, line works on the explanation part. That is the meaning of model agnostic. Model agnostic meaning it can work on any any algorithm. Third, we have a gradient-based method. What is this? These are all later developments that has happened in XAI. The early developments was the first 2 techniques. The recent developments is the gradient-based and interpretability by design-based. So what exactly is gradient-based? Now, once you build a model gives us the prediction. Now you will ask on what basis you have given this prediction. Which are the features that the model has looked into for a prediction. Then if a model has to give us the explanation, it will compute the gradients. So by computing the gradients or with the help of gradients, the XAI technique will tell which are the features which have contributed the most. So in this, the following are the methods that we have. In today's session, we will see the first algorithm that is developed based on gradient-based. GradCam is what we will look into. So once we understand GradCam, understanding the following methods becomes very easy. So all the other methods are built based on GradCam. So we look into GradCam today. And the last method what we have is interpretability by design. Under this we have CAMs. And what exactly is interpretability is? This is a special one. Not on all methods or not on all algorithms it works. It works only on few specific algorithms. So because of this, it is not very extensively used one. So we will not look into the last part. So we will take one from each of this. So we will see line, sharp, lime, and GradCam. We will look into these three methods in today's session. So I hope so far it is clear. It is clear so far. So let's move on. Now, I'm just showing you one example why one has to focus on. This is an result of a simple CSV file, and this is the result from my research work. Here we are we have taken a data set, on ovarian tumor data set. And in that, there are many parameters we have considered. We had considered clinical data. We had considered an, blood test. We had taken a certain ultrasound test, CT scanned test. There are so many tests that we had considered. And we had prepared the data using in a CSV file. Now, for that, an ML model was built, and the ML model has given us some percentage of accuracy. Now, we wanted to understand which are the features which has contributed for models of prediction. So we had used LIME, and the LIME has given us this particular result. Now, if you look into the left side of an image, if you look into now why the model has given 98% accuracy is, which are the features it has looked into? It has looked into the following features. It has looked into loss of appetite, abdomen disjunction, CA19, CEA, CA125. It has looked into these features. And if you see loss of appetite, there is no loss of appetite. There is no abdomen disjunction, there is no pain in the abdomen. And the CA19, CEA, CA125, these are cancerous biomarkers. All these values are very, very small values. Age is less, menarche is 13, menstrual abnormalities, family history, the person is not having family history, there is no question of cancer in the family. Then there is an menstrual abnormalities, yes. So if you look into all of these parameters, anybody who knows little about this disease, they say that the person does not belongs to cancerous one. It is a benign category. Now, look at what model has explained. The model also is saying I'm 99.1% confident that it is a benign. Why it is a benign? Because all of these features are, all these features are responsible for me to say that the particular belongs to benign category. Now, it just to give this explanation. So this is how you get the result. Now, when we copy this and paste to our paper, and when we have to explain, we should now know what are these numbers. Why did the model has given plus 0.2? Why did the model has given plus 0.16? What is this value 0.339? What is the 0.991? Only when we can able to understand each of these, then we can give an interpretation to this very easily, right? So that is what we are going to do today. We will understand the core working mechanism of SHAP, LIME, and GradCam, because you get a result something like this. So once you get a result, you really need to understand why all these are negative numbers. What is the meaning of negative? Why this is considered as a positive? And why, it just give this explanation. And what are different packages we have? If you are working on a SHAP, and if you're working on tabulated data, that is somebody who has just started their research and you're working on CSV file, or you have a data which is a tabulated data, then you can use all of these packages. You have these packages. Using these packages, you just get the result. But backend, what is happening, we will understand. Then if you're working on image-based data set, then we have these algorithms, these packages you can apply. If you're working on text-based data, we have these packages. So why we chose to go for LIME and SHAP here is, at the most, we will be working on these kind of data only. We have very less, it's wrong statement. Even if you're working on audio files and video files, you can still convert that into an image frames, and you can work once again on CNN-based algorithms. So for any of these kind of data, LIME and SHAP works extensively well. Because of this, we have chosen to cover these topics in today's session. So let's get started with understanding the core working mechanism behind the SHAP. Why those numbers? What are those numbers? So we will understand that. And what is the input that we are taking? Here, input is an image. Now, whenever we take an image, for an image, the features are every of the pixel values. Every dot in an image is actually a feature. Now, what exactly SHAP does is, first it will take an input. Now, it will divide input into multiple segments. It is going to divide it into multiple segments. Now, how many segments it has to do? It is internally, it is going to do so many classifications, so many segments. Now, each of this segment, we call it as a superpixel. Now, you can ask the question, why are we doing it? Now, ultimately, you are building a CNN model, right? So CNN model, you are building first to get the prediction, either 70%, 80%. After that, you will apply explainable AI method. So for a CNN, if you just give a single dot, a single pixel, can it identify anything? Answer is no, right? Because single pixel does not tell what is that feature, but group of pixels, probably it will identify that, okay, it is an eye, or it will identify that it is a straight line, or it will identify that it is a heart. So we always consider an superpixels or a segment here. Why? Superpixels is treated as a small region of an image where all the pixels, similar pixels are grouped together. And why is that we have to do? A single pixel has no meaning to a CNN. With one single pixel, CNN does not understand anything. Therefore, we take it as a superpixels. Why superpixels? Because it is a collection of many pixels, so that you can able to capture certain edges, shapes, textures. So that is more visible in superpixels than a single pixel. So in short, what is the first step? Take an image, divide that image into superpixels. So the first step is take an image, divide into superpixels. Then, now with this, you have from this portion, you have reached to this. Now, what is that we are going to do? Once we get many number of segments, we create a perturbed version. What do you mean by perturbed version? It looks something like this. What is this? Some portion of an image, you close it, you mask it, and some portion, you keep it. So how is that we have done this? Some portion is visible and some portion is not visible. Here some portion is visible, some portion is not visible. So create an perturbed instances or perturbed version. First step, take an image, divide that into many number of segments. Is there a limit for number of segments? Answer is no. So leave it to the model based on the size, based on the dimension, it is going to divide into number of segments. Then it is going to create an multiple perturbed instances. And what is perturbed instances? Some segments are masked, some segments are not masked. So some are visible, some are not visible. Then build an, you would have already built a CNN model, right? So for that CNN model, take the original image. This is original image where nothing is disturbed. That original image, you pass it to CNN and get the prediction. So the probability that the model is predicting this as a tree frog is 0.94%. I mean 0.94 probability or 94%. So on an original image, when your CNN model was built, it is giving us 94% accuracy. Now you have created a perturbed instances. So pass each of this perturbed image to that CNN model that you have built, same CNN on which you have tried the original image. Now pass a perturbed instances. You get the probability for each of these. Now, when you see the last image here, only some portion is hidden. Majority of the image is still visible, right? That's the reason you see it is giving us the very good probability. Here, most of the, in the second image or middle image, if you see, most of the part is being masked. So just by looking at the eye, here, can you tell it is a tree frog? Definitely no, right? So the probability that it is saying that it is a tree frog is very, very, very minimal. And here some portion is visible, some good portion only is visible, but still we are not very confident that it is a frog. Therefore, it is giving us the 50% of probability. So this is what is the first step. Build a CNN model, pass it to original image and get the result, and pass all the perturbed instances and get the result. So then the next step is, this is the core algorithm of SHAP. SHAP is going to give us the SHAPI values. You remember in the waterfall model, we had seen some numbers. So which means they are the SHAPI values. So how are those SHAPI values calculated? The SHAPI values are calculated using this particular formula. This is the core math which run behind. Now let us understand this math, and let's take one example and solve the problem. So here, what this formula is going to tell, how much one feature is contributing for model prediction. So that is what this SHAPI value is going to tell. So this symbol is the SHAP value for a feature I. That is what, how much did the feature I has contributed to final prediction. That is what is this particular one does. In this, what all other parameters that you are looking into, or what are other variables that we are seeing? Are we seeing F? We are seeing S. Now, what exactly is F? F is a set of all features. Now, you can ask the question, what are features here? When you take your tabulated data, the features are your columns. When you take an image is divided into many segments, right? So each of that segment here is a feature. So F is a set of all the features. Now, next is yes. What exactly is yes? Yes is a subset of the features that does not include I. So this theoretical statement does not make any sense. Let's take an example. Suppose you have an image. Look into this. You have an original image. That original image is divided it into 3 segments. Let us assume you have, just for understanding, we are dividing that image into 3 segments. Therefore, what exactly is S here? Now, S says subset of features. F here is a 3. It includes all the features. What is S? S is a subset of a feature that does not include I. Now, if F is ABC, when you say I is equal to C, then what are the subsets? The possible subsets are, first you write when the set is having an element A, B, C, write all the possible subsets. Is it not the possible subsets are null set A, B, C, A, B, AC, BC, ABC. These are the possible subsets. Now, what exactly is yes? Consider only those subsets which does not include that particular feature C. I hope you're understanding this. So what is S? S is all those subsets which does not include a particular feature. So that is the meaning of S. So I can pause here for a minute, for a few seconds for you to analyze what exactly I have explained. However, I'll take up the questions towards the end. What we have explained so far, F is a set of all the features. S is that subset which does not include a particular feature. Now, you can ask the question, why are we doing it? Ultimately, what is your aim? The aim is which feature has contributed the most. If that is the case, how does the SHAP works? If you have three students, now you want to understand among those three, who has contributed more for the project so that that particular student will get more marks. Rather than giving the same marks for all the three students, we will give only, we want to differentiate. We want to give more marks to that student who has really contributed more. So in that case, how is that you will be doing? You will now do a combination because we have no idea who has done what. So we will take that particular student and we will see, we will take out that student and we will see remaining two how much they have contributed. Then we will put that student into the group and we will see how much they are performing. So with that, are we not understanding the person, now say for example, we have ABC. And by having ABC, we have got 80% accuracy. Now you have removed A. And then now what is left out? You have left out with only BC. Now you are seeing that the performance has come down very badly. With this, are we not understanding A is contributing a lot? So similar way, the SHAP works. SHAP wants to identify which are the features which has really contributed a lot. So for that, it is going to consider all those subsets, combination of all those subsets by including and without including. That is what is S. Now, then let us look into this portion of an formula. And what does this portion says? This says how much does the output change when you add that feature to the subset. So that is what this portion of an formula says. And we have this fraction. Anything when we divide, we get a fraction. This fraction says how much weightage that has to be given to a particular subset. So don't worry. For the first time when you are listening, it is highly confusing. Let's directly go with one numerical example. You'll be able to understand each of those. Now, we have an input image. This input image is, first step is you have to divide that input image into number of segments. For an understanding purpose, let us assume that you have divided it into 3 segments. So what are those segments? Segments, we also call it as superpixels. Superpixel A, B, and C. So A is, we have taken only the face part, and B is, we have taken the body part, and C is, we have taken some portion of this heart. We have divided the image into 3 parts. Now, what is the first step here? Now, you have to consider all the possible subsets. So, when f is equal to 3, the possible subsets, we know that it is 2 to the power of 3. So, we get 8 such possible combinations. Now, what are these? These are those perturbed instances where first you don't have any pixels kept. Then A is you just kept only superpixel A. This is how it looks. Rest of the portion of the image is masked. Then B, you kept only this portion of an image and rest of the portion is masked. When you take C, you kept only this portion of an image and the rest of the portion is masked. And so on and so forth. When you write AB, only these 2 portion of the image is there, rest is being masked. And the ABC says all of the portion, all of the image is there. So I hope you have understood this part. Then you have already built a CNN model. Now pass each of these image and get its probability. Pass only this and then get the probability. So when you kept only A, the probability that it has predicted as tree frog is 0.7. When you pass this particular image, second, where only B is there, when you pass this image, the model is giving, because just passing the body, can we say that it is a tree frog? No, the face can be anything. So it is only 50% confident that it can be a tree frog. Now, C, it is only a heart, but some portion of hand is there. Therefore, the probability that it is saying tree frog is very small, very less. And the AB, when you pass this, no, okay, it is little confident, it is giving you 75%, so on and so forth. So what did we do? We have divided the image into segments, and we have created multiple perturbed instances, and we have passed it to CNN to get the predictions. So once this is done, now we are calculating the first portion. The fraction portion is what we are calculating. This part of the formula is what we are looking into. What is F? F is a set of all the features. How many features here? Super pixels are 3. Therefore, F is 3. If F is 3, cardinality of F is, So F is ABC. Set is ABC. Number of elements in the set is 3. Now, what exactly we are doing next? You see here, when you consider this subset, what all, how we can explain this subset? Can I say I have a subset where no features are being present? I have some subsets where there is only one feature present. I have a subset where only two features are present. And I have a subset where all the features are present. Is it not? We explained that. So that's what we have done. We have considered first, where there are no elements, no features considered. So cardinality of S is 0, which means there are no features at all. I'm talking about the first part. Here, there are no features that are considered. What is the weightage that I should give for this subset? So what weightage you are giving? So look at the formula, how we have to calculate. So S, cardinality of S here is 0, right? So that is where you have 0 factorial. Then substitute cardinality of F is 3. 3 minus 0 minus 1. So 2 factorial. So it is 2 factorial. Whole divided by, it is F is 3. Cardinality of F is 3. So 3 factorial. So do a simple math, you get 1 by 3. Now, we are talking about these, we have a subset which is having only one feature. How much weightage you have to give to this subset? So cardinality of S is 1. We are taking where subset having only one element. So this portion is 1 factorial. This is 3 minus 1 is 1 factorial. Whole divided by 3 factorial. You get 1 by 6. Then we are talking about the set containing 2 elements. If the set is containing 2 elements, then the weight is 2 factorial. Then this is a 3 minus 2 minus 1. So it is 0 factorial divided by 3 factorial. Now, you can ask the question, why is that we have not considered where it is S is equal to 3? I'll ask this question towards the end. I want you to think about it. I'm saying we will not calculate for cardinality of S is equal to 3. We are not considering this. So I want you to think about it. Why? Because you think about put the value back into the formula, you will get an answer. When we are considering S is equal to 3, we have factorial cardinality of F is equal to 3. 3 minus 3 is 0. 0 minus 1. What is minus 1 factorial? We don't have an answer, right? So the algorithm doesn't know. And the next is when all the features are included, then why is that you need to understand which feature is important, right? So that is the reason why we don't calculate for S is equal to 3. I hope you have understood the first portion of an formula. The next part, look into the next part, how we are calculating. So here the next part is, now this part we have calculated. Now, what exactly is this? Look into, now we want to understand superpixel A. How much superpixel A is contributing for models of prediction. Now, 3 superpixels are there, A, B, C. 3 students are there, A, B, C. Now, we really want to understand how much student A alone has contributed for a project. If that is the case, we should now consider all those subsets where A is not part of it. Correct? So, where A is not part, if these are all the subsets that we have, write all those where A is not present. Is it not we get B, C, B, C? Rest in every place we have A. So now we are considering. So with this, we will understand what is the contribution of A alone. Right? So now look into this particular formula. How is that we are doing? Now we already got an answer for the first part. For this part, how is that you will write? What is S? S is a subset null. Here you have phi union. And what is A? What is I value here? I is A, right? So you write A. So a simple math. What is union? Union is, you consider everything. So null union A is A. So you are getting f of A minus f of S is null. So you got this. I hope you have understood this. Then what we are doing, f of A is just get the predictions. What is f of A value? 0.7 and f of phi value is 0.1. We have 0.1 value. So, a simple math, you get 0.6 and you take when S is null, what is the weightage that we are giving? We are giving 1 by 3. We have calculated some time back. So 1 by 3 into this number 0.6. This leads to 0.2. Now, what exactly, how is that you have to understand the meaning of 0.6 and 0.2. When only superpixel A is kept, the probability that you are predicting it as a tree frog increases by plus 0.6. And this weighted to 0.02. So, can you correlate on that waterfall model? You had that plus values. What are those plus values is what is the you have obtained here. Then let's move on. Let's take the second S is equal to B. When S is equal to B here, just go back and then substitute. What is S? S is B here. B union. What is I? I is A. So what is union? Union is including A and B. So that's where you got f of AB minus f of S. S is B, f of B. Just go back and then what predictions have been made. Get the answer 0.75 and f of B is 0.5. Then continue this calculation. When here there is one element that is considered. So when there is one element, the weightage that you have to give is 1 by 6. So you have put 1 by 6 and then you have performed the calculation. So after once you do the calculation, the last step here is add up all of these. Add plus 0.2, plus 0.04, add all of those contributions and you will get the final answer as 0.46. Now, what is this 0.46 answer is the superpixel A, that is the frog's face, has contributed 0.46 to the model's final prediction. So it is giving out of 3 superpixels A, B, C, A alone is giving 0.46 to final models of prediction. This is how we interpret. Similar way, now do it for B. So which means the total features are A, B, C. Now I is B. If I is B, take out all those subsets where B is not present. Now, you have 3 students. You have seen how much A is contributing out of those 3. Now, you will take a second student, B student, and then you will see what is his contribution in this group. So now take out all those subsets where B is not present. So when B is not present, is it not these are the possible subsets? Null, A, C, and AC. So similar, same calculations you do. And the B contribution here is 0.28. A's contribution was 0.46. Now you thought probably this is only 46% A is contributing, which means B and C, someone is performing very well. That's what you have thought. So now you have included A and then you are seeing B's contribution. And then you have understood B's contribution is only 0.28. Similar way, do it for C. So the same calculation, same math, do it for C. And the C contribution is only 0.06. So what did we understood with this? Is it not the final Shapley values here are the superpixel A is contributing a more 0.46. Superpixel B is contributing 0.28. Superpixel C is contributing 0.06. So what are superpixel A, B and C? Is it not A is a phase? So this portion is the one which is contributing a lot for models prediction. And then the body, and this is hardly making any contribution. That's the reason you are getting this. Now, you have to ask the question, how much I can now trust this? Okay, SHAP has calculated some values. Can I really trust these values? Can we really believe? We always, one doctor has told that we have been diagnosed with so and so. We don't trust the doctor. Then what we'll do? With all those reports, we go to another doctor. And if that doctor also says, yes, you have been diagnosed, then this is how we trust. So here we don't have another model. We cannot go to another doctor like this. So what we have to do, we have to go for a consistency check. What is consistency check here is, now do the subtraction of, when you include all the features, the answer is 0.9. When you don't include any features, the answer is 0.1. So minus it, 0.9 minus 0.1, you get the answer 0.8. What did we do? We have done the subtraction between these two. By including all, by including none, you got 0.8. Then SHAP has calculated some values, right? Add up all those. When you add up all those, if you still get 0.8, which means you can trust those SHAP values. I hope this is clear. Now, why is that you have to do this? Because SHAP follows something called as a cooperative game theory principle. So that cooperative game theory principle is the contribution of all features must add up exactly to the model's output difference. So when we get this answer, which means there is a consistency, you can able to trust these results. So this is how you will look into this 0.8. The total models of prediction must be contributed fully or must be distributed fully among these features. Now 0.8 has to be distributed. So how is that it is distributing? 0.46 it is given to superpixel A, 0.28 it is given to superpixel B, 0.06 it is given to superpixel C. Now, is this completed? Answer is no. The final answer is this heat map. It has to generate a heat map. So you see, this is how you get the answer. For an features, for a tabulated data, you get something like a waterfall model. But here we are dealing with an images, right? When we are dealing with an images, we get something called as a heat map. Heat map is, whatever is the size of the image, the same size you will have one more, and there it is going to highlight which are the pixels which are contributed more. Now, the entire image you have divided it into three, A, B, C. Now A has the highest contribution 0.46. Then this portion B, which has the next contribution C. Now, whichever has got the highest contribution, all those pixel values will get the strong red color. So now when you take this tree frog, this entire pixel values, all these pixel values will have a strong red color. Then the next contributed value is B portion. This portion of an image will have a light, little more lesser intensity. And this is hardly contributing. Therefore, you will have very light contribution. So this is how you will interpret. Now, when you are writing a paper, research paper, if you can understand this math behind, so once you get a result, now can you able to see that, wherever there is a darker pink, can you say that this is the portion which has contributed more for model's prediction? Now, you can also say that sometimes you will have a negative contribution also. When you have a negative contribution, negative contributions will be shown in a different color. Here, SHAP by default takes blue. So it is, and some pixels are neutral. It does not contribute anything. Those will be towards exactly white 0. So this is how you create an heat map, and this is how the SHAP works. So let's move on to line. Line will be a little faster because most of the concepts will be similar. Line, when you apply it on an tabulated data, we get a result like this. So here also, can you able to see there are some values? There are some values. So we will understand now the math behind why these values are coming. Later, we will see how to interpret this. So for a particular feature, the model has predicted it as benign. Why model has predicted it as benign? Because there are most of the features which are negatively contributing. Only two features are positively contributing. Therefore, we are saying that it is benign. And second, for one more feature, the model is predicted it as border case. Why it is border case? Out of features, there are exactly 50% of the features which are saying positive. There are 50% of the features which are saying negative. So it is half and half, right? Therefore, the model has predicted it as a border case. So line also gives us some values like this. So what exactly is the math behind the line? And what is full form of a line? Line stands for local, interpretable, model, agnostic. Okay, so that's what is the line. Even if you just search in the internet, you will get it. So let us get into the math behind how exactly line works. Same concept like SHAP. Take the image, divide the image into many segments. Now, the only one difference here is, here also you create many perturbed instances. Now, the only one change is, whichever the pixel that you are keeping, you will make that as 1. Which pixels you have masked, you are making it as 0. So, which means those which are on, which you are keeping, will be having 1. Which you are not keeping, you will have the value 0. So I've given an example here. You can see this. That is the only one difference in the data part. Which you are keeping will be 1. Which you are not keeping, turning off, you are making it as 0. Okay, if you have divided a pixels, if you have divided an image of 50 such segments, then you will have an image of length 50. You will have a single vector of length 50, and that 50 will be having a combinations of 0 and 1. Which portion you kept will be 1, which portion you have not kept will be having 0. Okay, so once you get that, this is the table that you will be doing it. What is this table? So once again, how many superpixels? For an example, instead of taking 50, we are taking 3 such segments we have done. First step, take all the combinations, 2 to the power of 3. 8 such combinations you get. What are those 8 such combinations? We have already seen it. But here we are dealing with line. So line, what you are keeping, you should make it as 1. What you are not keeping should be 0. So none indicates you are not keeping anything. So all the values will be 0. A, you are keeping only superpixel A. So can you imagine keeping only superpixel A? How does it look? Sometime back we had seen there is an image where only the face portion is kept, rest all portion is masked. So that's the meaning of it. So you are keeping only A. So how will you write? This is, you kept it. So 1, there is no B, there is no C. Okay. Then B, there is no A, there is B, there is no C, so on and so forth. So we are creating this data. Now, once you created this, you are going to, you have already built a CNN model. So for that CNN model, you pass all these perturbed instances. and then get the prediction. So this is how you have got the prediction for each of those images. Then calculate the difference. How is that you calculate the difference? You now need one sample where you are keeping all of the pixels. When you keep all of the pixels, is it not, you will have an answer 111, right? When all the superpixels are kept, the answer is 111. Right? Now, take the difference. How will you take the difference? Difference between these two. Here, none of the pixels are kept. Here, all the pixels are there. So, take the difference between these two. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 0 is 1. We got this difference. Take the second one. It is 111 minus 100. So, 1 minus 1 is 0. 1 minus 0 is 1, 1 minus 0 is 1, and so on and so forth. You have calculated the difference. Then get the Euclidean distance. How will you calculate the Euclidean distance? Here, take under root 1 square plus 1 square plus 1 square. It is 1.7. Under root 0 square plus 1 square plus 1 square. So take the, calculate the Hamming distance. So I hope it is clear to you. So how did we do? Under root 1 square 0, under root 0 square plus 1 square, and so on and so forth. You have got the distance. So next, once we get the distance, the next step we have to calculate the weight. How is that we calculate the weight? This is the formula to calculate the weight. Weight is equal to exponential e to the power of minus d square by lambda square, or sigma square. So what is this one? This we call it as kernel width. And what is the kernel width? The original line, the author who has invented this, he had used the formula as this. 0.75 into square root of d, or under root d. What is d? D is the number of features. So what is number of features? How many features we have considered? 3 features we have considered. So under root d, under root 3. 3 under root 3 multiplied with 0.75, we get this value. And here it is square. So take the square of it, you get this value. So now we have to calculate the weight. Weight for the distance, d value is 1.732. Take the square of it, take the, do this component, and e to the power of minus 1.77. You get this weight. So I'll pause it here for 5 seconds. You can see the calculation part. Okay. So how did you get, so what is that we are understanding? Can you observe ultimately what we have calculated is the weight. So for some weight is more value, for something the weight is less. Can you interpret for what the weight is more, for what the weight is less? Can you see here the weight is more here, W is equal to 1, for which when D is 0. When D is 0, what is the meaning of this? All the features are being kept. So, which is closer to all the features, for that the weight is high. So, kernel gives the higher weight for those samples which are closer to the original instance. What is original instance? Where all the pixels are being kept. And lower weights for those which are far away from the original one. So, which is a smaller value here? The smaller... Yeah, so go back and then see where the value is very small. Is it not here? The value is very small. For what? For D is this. For D, this, which means there are no pixel values which are kept. Definitely, this is something which is far away from the original one. Therefore, this has given, the model has given less weight for it. I hope this is clear to you. Once this is clear, the next is a basic of ML. What is the basic ML? We have seen linear regression. So for interest of participants, I'm quickly doing a revision of linear regression here. So what is the linear regression? Now we have age and experience. Now we want to understand what is the salary. So is it not, there is some correlation between x1 and x2. There is a relation between x1, x2 and y. There is a relation, right? If age is so much, if experience is so much, then the salary is less. If age is more, if experience is more, salary is high. That means there is a relationship between X1, X2, or there is a relationship between the features and then the label. So now, if you can understand that relation, then whatever the new instance you get, you'll be able to tell what will be the salary, right? So all what we need is you have to understand that relationship between X1, X2 and Y. So the simplest way to find out the relation is using a straight line. What is a straight line equation? Y equal to mx plus c. But here there are two features. So the y value can be write in this way. Instead of writing c plus mx, can I write it as c is equal to mx1 and mx2? Can we write in this way? Or m1x1 plus m1x2? Why? There are two features. So we have written this. Now, if we can find out the beta naught, beta 1 and beta 2 value, if we know, if we can get the best values for these, is it not you have understood the relationship between x1, x2 and y? So the best values of beta 1, beta 2, beta 3 actually describes how x1, x2 and y are related. Now the question, how do we find this? Then regression finds the best values. How do the regression finds the best values? Can you, if the difference between the ground truth and the predicted value, that is y and y hat, if this difference is very, very less, then is it not your beta naught, beta 1, beta 2 values are very good? So our aim is to find beta naught, beta 1, beta 2 values. How do we find these values? If you can find the difference between, if you can minimize the difference between the ground truth and predicted value, this y naught or y hat is actually the combination of all three. If we can have this less difference, is it not we actually got a good values? So now, how do we minimize this error? So we calculate, we use something called as gradient descent. Gradient descent is that algorithm whenever you want to find the best parameters. And how do we take? We compute the gradients of it. So by computing the gradients, so by substituting the values back into it, is it not we get the best beta naught, beta 1 and beta 2 values over a period of time? Once we get this best beta naught, beta 1, beta 2 values, we have understood the relationship between x1, x2 and y. The same concept of linear regression or multilinear regression is used in a line. But only one difference is it is weighted linear regression. So what is weighted linear regression? So here the aim here is ultimately to get that beta naught, beta A, beta B, beta C. Why beta A, beta B, beta C? Our features are A, B, C, right? So if we can get these coefficients, that's sufficient. So now same regression concept is used, but what we have adding additional is that weighted regression. So what is weighted? Here this is additional term which we are including. So if by minimizing this error, weighted loss is what we need to minimize. Now, say for example, we have got these coefficients. Now you can ask the question, why are we deviating? We are not deviating. Our aim is still to identify which among these features have contributed more. How many features are there? Superpixel A, B and C. Out of these three superpixels, which superpixel has contributed more? Have we not got the answer here? See, the answer is 0.41. For beta A is 0.41, which means superpixel A has the highest contribution, then superpixel B, then superpixel C. So how is that you will analyze this? Now the line explanation is just those beta values. If beta A is highest, therefore that is a strong positive influence. Then the next superpixel. So this is how the line works. And what exactly is these values? Initially, we have seen in a line, you get some values, right? So those values are actually these values. So let me go back and then explain you this. Now, uh, uh, for this particular explanation, the model has predicted it as benign category. Why model has predicted it as benign? The weightage that it has given, see, loss of appetite is 0, and the CA 125 value is so much, CA value is so much. Abdomen disjunction, there is no abdomen disjunction, no pain at all. There is no loss of appetite. There is no family history. And CA 19 is very less value. So is it not all these 4 features which are highlighted in blue, is it not these are if we have these kind of values, is it not they actually belong to benign category? So, and what is the weightage that the model, model has given to each of these features? Can you see 0.73? This is that beta value. So this is the weightage that model has given to this feature. This is the weightage that model has given to this feature. This is the weight. These are those coefficients what weighted linear regression gives. So this is how we need to explain, and this is how it works. Yeah. So let's get into the last method called camps. Okay. Now, you can ask the question, the minute when we say grad cam, the grad cam full form here is gradient based. Okay, so when you see that word gradient, don't think that we are backpropagating and we are updating the weights. No, here we have already built a CNN model, and it is well-trained CNN model, which means during training phase, you are updating those weights, kernels, you have backpropagated. Training is done. Now, once the training is completed, you are now passing one test image. During testing phase, you are passing one image. For that image, the model has contributed, the model has predicted that the given image is benign or the given image is malignancy. Now you are asking why the model has predicted, or you are asking a question to CNN. But unfortunately, CNN does not has the capacity to answer. CNN will only give you the accuracy. How much, what is the accuracy? It can extract the features. It can shrink the features. It can flatten all that operations it will do. But if you ask the CNN model that you have given 98% accuracy, can you explain which features which features have contributed? CNN does not do it. That is where now you want to achieve. You want to find out which features have contributed. So when you ask the CNN to do it, CNN cannot do. Then what the CNN will do, it will take the help of some methods. Now, for those methods to explain, it will ask these methods, this grad cam or guided backpropagation cams, it will tell CNN, do only one time backpropagation, come back, do backpropagation. Now, this backpropagation is not to update the weights. Why do we do the backpropagation? We do backpropagation to get the gradients. Now, once those gradients are computed by the CNN model, then these grad camps or guided backpropagation or not camps, it is these 2 algorithms which comes into the play to tell which are the features which are important. I hope you have understood this portion, because often when we explain this to students, because of the word backpropagation, because of the word gradient, they often ask this question, ma'am, are we updating the weights here? That's when I realized that, okay, students are getting confused with these words. No, already it is well-trained CNN model. For that trained model, you are now passing one image. For that image, you are asking which features have contributed. Now, CNN cannot explain. So now CNN is taking the help of GradCam, guided backpropagation. Now, what these methods will tell, it will tell CNN that do one backpropagation, compute the gradients and give those gradients to me. And with the help of those gradients, I will tell which are the features which are contributed. That's how CAMs and, grad CAM and guided backpropagation works. So let's understand. So what is the full form of grad CAM? Grad here is gradient weighted. That's a full form of grad. And CAM is a class activation mapping. So it is a model specific XAI method. Why it is model specific, that we will see. Now we will understand how does it works. Let us assume we have an image. For that image, we have passed a kernel. So what I'm explaining now is you should go back and then relate it to CNN. So when kernel is applied to an input image, what we get? Is it not we get the feature maps? What is that feature map? Kernel will go through the entire image and then you will perform a convolution operation and you get a values, right? Those values are the feature maps here. Now, inside all of those values, we call it as an activation. Each of these feature maps, we call it as a channel. So these are the terminologies that you should remember. Now, GradCam will work on these. So what does GradCam wants? It requires it depends on convolution layer. It requires on this, it depends on this feature maps, the values in these feature maps, and the gradients which flow through these feature maps. Now, why GradCam is called model specific? Now you tell which are the models we have with us, which will actually give us the feature maps. Can ANN give us the feature map? Does our machine learning algorithms give us the feature map? Is RNN LSTM give us the feature maps? No, it is only the CNN which has the capacity to give the feature maps. What is feature map? Input, apply kernel, do element-wise multiplication, summation. So whatever is the result that we get, that is the feature map. So only CNN performs that. Therefore, GradCam is something which works only on if you are using an algorithm as CNN. So GradCam does not work on your ML algorithms. It does not work. Therefore, GradCam is called model-specific XAI method. It works only on CNN-based models. CNN-based models. When I say CNN-based, wherever you are performing convolution operation, all those algorithms you can apply GradCam. You can use UNet. You can use object detection algorithms. Wherever there is a convolution operation, use GradCam there. GradCam works there. So what GradCam gives us, it is an explainable AI technique that is going to highlight the regions in an image. It is going to highlight the regions in an image which are most important for model prediction. And how it is going to do that, let us see. Okay, so from this diagram, what are we understanding? There is an input image. Input image is passed to first convolution layer. It is passed to second convolution layer. It is passed to last convolution layer. When I say the convolutional layer, what all things are included? Convolution is included, ReLU is done, and pooling is also done. If you say pooling you don't want, then you understand it as convolution and ReLU operation is done. So to the last layer, you are applying a kernel and you get the feature maps. Now, the important question one has to understand is, why are we taking last feature maps only, last convolution layer feature maps only? Why are we taking? Why are we not bothered about the first layer, second layer? What is the answer? Go back to your sixth session. On that day, we have seen CNN is being inspired by human visual system. In human visual system, we have visual cortex V1, V2. Those are all initial layers. Initial layers are responsible for what? Extracting a simple features. But here, what is your requirement? Which input features are important for model prediction? That is your requirement. If that is your requirement, with the initial level, you are only extracting simple features. Which layer is responsible for extracting more deeper features? Is it not the last layer, the deeper layers? Deeper layer here is the last convolution layer. That is the reason we take the feature maps of last layer, but not at the initial layers, because your aim is to understand which features have contributed. If which features have contributed for model prediction, last convolution layer extracts good features. Initial layers are focusing only on simple features. So on those simple features, the feature map, if you apply GradCam, then do you think that the final result, which features have contributed most, do you think that it gives us a good result? Answer is no, right? That's the reason we go for a last convolution. Then whatever the features maps that we have got, convert that into flattened layer, apply it to a dense layer, and finally you get the output. Now, what output? During a testing time, see the word, during testing, you passed one input image. That input image is going through the entire convolution, a forward pass. So at the last, it is going to give us the output. So just before the output, see here, I'm taking YC. YC is called logit. What is logits? Logit is just before you pass to an activation function, that summation value. In the dense layers, in the last output layer, you will have an neuron. In the neuron, you will have a summation value, and then you will have an activation function. Just before you pass to an activation function, whatever is the summation value, that summation value is called logit. Logit or logits, pronounce in however way it is. Logit is what you take it. Now, this YC is very important to us. And why we choose this YC? The whole calculation depends on that YC only. Now, during testing, the model has predicted the given image as pneumonia. Now, if the model has predicted it as a pneumonia, now which class it has predicted? So if at all, if it is a multi-class classification, at the last output layer, you will have 3 neurons. Now, in the 3 neurons, say for example, this is pneumonia. This is non-pneumonia. This is something else. This is where the class is. Now, if this is the output the model has predicted, you will take its summation. You will take the class it has predicted, its logit is what we take. Okay, that's what is YC. So in the forward pass, we got the feature maps, and we feature maps of last convolution layer only. Why last? You know it. And then we take the logit. The output to scores logit is what we are taking. What are these? These are the last layer ka activation, feature maps. So let us assume those feature map values look something similar. Now, CNN, if you ask which values are important, CNN cannot do it. So what CNN is taking the help? CNN is taking the help of GradCam. For GradCam to tell, GradCam wants the gradients. So now what GradCam will tell to CNN? Come back and do one single back propagation. When you do a single back propagation, it will do a back propagation. It will compute the gradients here also. It will compute the gradients here also. But GradCam does not need any of these gradients. What GradCam wants is when it computes the gradients with respect to each of these values in the feature map. So gradient derivative of YC with respect to every of the value which are present in this feature map A1, A2, and so on up to AK. I hope you are getting. I know it's too heavy, but it's important concept. Simple. You have the feature maps. Take the gradients with respect to every of the values in those feature maps. So let us assume you have got this value. What we are doing, we are taking a YC value we know. We know each of these values. Just take the gradient derivative of YC with respect to 2, derivative of YC with respect to 1, and so on with respect to each of these values. You get one number. Put that number. The next step here is take the average, add up all of these values, divide it with the number of such values. So what is the math behind? Summation of ij. What is this? When I value is 0, j value is 0, you are in this. When I value is 0, j value is 1, you are here. When I value is 0, j value is 2, you are here. When I value is 1, j value is 0, you are here. So on and so forth. So take each of these values, add it, divide it with, you're taking a mean of it. You are dividing it with what is z? Z is number of such pixels. How do you get number of such pixels? Is it not height into width? So what are we getting? We are getting how much weight that has to be given for this particular feature map A1. Okay, so this is what we have calculated. How much importance has to be given to this feature map? Now we'll come back to this line. So what we have done, we have taken an feature map, we have computed the gradient, we have added each of those values and we have divided it with the 25. Take the second feature map, compute the gradient, you got this. Take the third feature map, you compute the gradient, get the weights of it. Now, what is A1? A1 is so much, A2 is so much, A3 is so much. If you observe, you see here, A3 is more than A1, then A2. On what basis you are saying that A3 is more? Can you go back and then look into A3 is 0.3. Why did we get 0.3? Because all of these gradient values are positive and the values are high. If you look into, these values are very small. A2 is small. Why? Most of the gradients are negative. And whatever the positive gradients, those values are small. That's the theory that is written here. If the gradient is large and positive across many locations in the feature map, then that feature map is very important for the prediction. Thus, you give a larger weight. I hope this is clear to you. So next step, you have to create a heat map. So now you have to visualize. How do you create a heat map? What did you do so far? You have taken the feature maps of the last convolution. You have computed the gradient. You have calculated the weight. What are those weights? The weights are A1, A2, and so on up to AK. The next step is multiply each of these weights, multiply A1 with all the values which are present in A1. Take A2, multiply with all the values which are present in A2. Take AK, multiply with all the values which are present in AK. So, and then perform an element-wise addition. So multiply each feature map by its weight and then add them element-wise. You get something like this. Now, what is your ultimate aim? Aim is to understand which are the features which have positively contributed for model prediction. But you have some negative values here. How do you remove the negative values? Is it not we did this operation? You have performed an element-wise addition, that is where summation, and then you have multiplied each of the weight with its associated feature map. Is it not this operation we did? And we got some negative values. Because it is negative values, pass it to ReLU. So which means for this entire, you are passing it to ReLU. Then you get all positive values only. Then use some color encoding, and whichever the values which are more, give a brighter color. The values which are less, give less color. Zeros, give black. So this is your heat map, GradCam heat map. If this is not clear to you, there is one mathematical one. You have a feature map, A1, A2, A3, because ultimate aim is which features have contributed most. Which features have contributed most? Where are those features? Features are there in the feature map. So which feature map has contributed most is what you are calculating. So, and then you have calculated the gradients, you have calculated the weight. So this step is multiply 0.132 with 2, 0.132 with 1, 0.1320, multiply the weight with every of the element which are present in A1. You get this. A2, multiply with every of the values which are present in capital A2. The weight A3, multiply it with the elements which are present in the feature map A3. You get this. Then add all of these elements. Add the first element 0.264, 0.052, 0.6, element-wise addition. You get this. Coincidentally, here all values are positive, but in real world, you will not have all values positive. Pass it to ReLU, then you get the matrix. Now, with this, what have we understood? Wherever the values which are high, it means those are the pixel values which have contributed. Now, the last step here is upsample and overlay. Now, this is important step. Heat map. Why are we calling it as a heat map for GradCam? Why we did not call heat maps for Lime and SHAP? All that we will discuss here. By the time you come to the last convolutional layer, is it not you have reduced the size of your feature maps? Initially, if your image is of size n cross n, after you perform the convolution, if padding is not applied, and then if you apply pooling, is it not you have reduced the size? Then again you passed it to convolution. Again you have reduced the size. Like that, if you have built a deeper neural network, by the time you come to the last convolution, the size has reduced. If the size has reduced, then finally the heat map, what you have got is the smaller heat map. Is it not you got this heat map? Now, if you see here, this is the combination of all the feature maps of last convolution. How? Yeah, I'm closing it. So if you take here, this is the feature map of first one, second, third feature map. So by multiplying, by doing the addition, we have got the last heat map here. I mean, you have taken the combination of all the feature maps. So this is only one feature map that we have. So which is the combination of all the features of last. Now, the same thing, if I put if I overlap on this, it's not correct because the dimension is changing. So what we will do, we will increase. We will now do upsampling, interpolation. You can use any of those techniques. Upsample it. This upsampling, you now you overlay on the original image. This is where you will see the region which is important for models prediction. Now the question is, why we are, Sujata ma'am, I'm closing it in another 2 minutes. Yeah, so why we are going for feature maps? Why not use flattened layer values? What is the reason that last layer feature maps we have used? You can answer it as in the last layer only most important features are present. Correct. After that flattened layer, you will take those feature maps and then make it as flattened layer. So which means important values are there even in those feature flattened layer also. But why we are not going for flattened layer? Why at the last feature maps only? Because ultimately, first answer is once you convert feature maps into flatten, we are losing its spatial relationship. Correct. And most important here, we ultimately want something in the matrix form only, so that when you convert that into, when you upsample and when you put overlay, it will be still in that image matrix representation only. So that, see, you are using the flatten, I mean, you are not using flatten layer, we are using feature heat map or features is because we want ultimately output in terms of this matrix one. The why we want in matrix form, because from here you can convert it to this. Once you can convert into this, you can overlay so that you can able to put it back onto the original image. That's what is written here. So this is how GradCam works. And on the medical images, this is how it looks, the output. I'm open for the questions. If you have any questions, you can ask me.
Ma'am, we have few questions in the chat box.
I am opening it, ma'am.
Okay.
What about time series data like ECG? Yes, we can, Nitya ma'am, you can still work on ECG. Then probably GradCam, all those later explainable AI techniques will not work. You can apply Lime or Sharp, which works perfectly fine for time series data. You can apply Lime and Sharp. Ma'am, it is good. Is it good integrate concept bottleneck based explainable deep learning to detect Norma? Is that topic good for PhD work? Hiral, I'm not sure what you're talking about. We can discuss about this in person, or I mean separately. You can we can discuss about this. See, bottleneck-based explainable deep neural network. You're talking about bottleneck-based is it can be UNet or it can be autoencoders. It can be variational autoencoders. This is what is my understanding. Bottleneck-based explainable deep neural network. So answer is definitely yes. But is it a good topic for PhD work? That depends on so many factors. What is the role of T1, T2 weighted MRI data set in MRI-based diagnosis? Please elaborate, madam. Harish sir, T1, T2 weighted MRI, these are all, whenever they take an MRI, there are certain settings that the radiologist will do before they take an MRI. T1 will cover some features. T2 will cover some features. So it's like before you take up, before you click some pictures, you do certain settings, right? So based on a setting, it is going to capture it. So on what you are trying to, what kind of features that you are looking into, accordingly, we select either T1 data set or you will go for T2 data set. Preferably go for T2 data set because T2 is something which is going to capture more detailed features also. Ma'am, can you explain once again what is S is equal to 0, 1 by 3, S is equal to 1, 1 by 6. Okay. Can we apply to RNN as data in a data generating sequence? RNN is not a generative model. Let me understand, Ushasri. Okay, how to apply for RNN as data is a time generating sequence data, madam. Okay, ma'am, if you are applying explainable AI for time series data, you can 100% apply there, but this gradient based algorithms will not work. Once again, you may have to go for Lime and Sharp only. Superpixel itself are called, yes, Swapna ma'am, superpixels itself are the features for an sharp line, etc. I am still yet to answer to Swapna ma'am's question. Please share the PPTs. Okay. I'm sharing the PPTs. Can you please tell me whether you can able to see? How should I go back? Can you see my screen?
Yes, ma'am. It is.
Okay, so Swapna ma'am has asked what is that S1, S2? Even if I teach orally, you may not be able to get. So let me go back to the slides. Ma'am, what is this S is equal to 0 means? Now, how much, go back to this. Here, what exactly is this fraction portion telling? How much weightage we have to give to the subset? That is the one. How much importance has to be given to a particular subset? Now, if you see, S is equal to 0 indicates a subset where no features are considered. That's the meaning of S is equal to 0. When S is equal to 0, no features are considered. When no features are considered, how much weightage that you should give to that subset. So when S is equal to 0, how are we getting? We are substituting back into this formula. Go back and then substitute the values in this. Here, cardinality of F is 3 minus cardinality of S. What is the cardinality of S? S here is 0 minus 1. So what is 3 minus 1? It is a 2. That is what is this portion. And what is 0 factorial? How did we get the 0 factorial? Cardinality of S is 0, right? So 0 factorial. Then divided by cardinality of F factorial. What is F factorial? It is a 3. So 3 factorial. And the simple math, 0 factorial is 1, 2 factorial is a 2, 2 into 1 is 2, 3 factorial is 6, 2 divided by 6 is 1 by 3. Now, S is equal to 1. When S is equal to 1, how much importance has to be given to those subsets which is having only one feature? That's the meaning of it. So, how much importance has to be given to these three? So, again, go back, S is 1 here. So, 3 minus 1 is 2, 2 minus 1 is 1. Therefore, you are saying 1 factorial. And S is equal to 1, so 1 factorial. I think this is clear now. Yeah. So, this is all about the topic for today's session. Yes, Sujata ma'am.
Yes, ma'am. Thank you, madam. On the behalf of AICT, ATAL Academy and SNIST, I extend our sincere thanks to Dr. Ashwini Kodipalli for a highly informative session today. Ma'am, your clear explanation of how artificial intelligence or explainable AI and emerging technologies converge to enable continuous monitoring and intelligent healthcare systems was truly insightful. The way you connected theoretical concepts with real world application and emerging trends made the session extremely engaging and relevant. We sincerely appreciate your time, expertise, and continued support in delivering one more session today in continuation to previous session 3 on CNN architectures. Both the sessions have greatly enriched the learning experience of our participants and added immense value to the FDP. Once again, thank you very much, ma'am.
Thank you, ma'am. Thanks for the opportunity given. I wish the participants great learning. In some occasion, we'll surely connect back. Thank you.
Yes,
Yeah.
thank you. Thank you. Dear participants, please stay back. Session 2 speaker already joined. Once again, good afternoon to one and all. It's my privilege to introduce our distinguished resource person, Mr. Shivakumar K.R., an innovator, researcher, serial entrepreneur with nearly 2 decades of hands-on experience in artificial intelligence and emerging technologies. Mr. Shivaram is an alumnus of IIT Delhi, where he completed his MTech in Control Systems, securing department rank 1. He is currently the co-founder and CEO of Innoverse Tech, where he leads the development of AI-driven products focused on job creation, skill development, and entrepreneurship enablement. Over his entrepreneurial journey, he has founded and built more than 12 technology startups, applying first principles thinking to solve real-world problems across domains such as healthcare, genomics, education, finance, robotics, drones, and AI-powered platforms. Prior to entrepreneurship, Mr. Shivaram spent over 10 years in the financial industry, working as a quantitative researcher and trader at leading global organizations, including Societe Generale, Edelweiss, Bank of America, and BRICS Securities. During his period, he developed high frequency trading, and cross asset quantitative strategies, with several models managing investments worth hundreds of millions of dollars. His technical expertise spans artificial intelligence, machine learning, deep learning, natural language processing, generative AI, robotics, IoT, genomics, and algorithmic trading. He has worked extensively with modern AI architectures, including CNNs, LSTMs, GANs, transformers, and large language models such as GPT-4, LLM, and Mistral, along with platforms like AWS, Azure, PyTorch, OpenCV, and Cloud Native Microservice. Mr. Shriram has led several globally recognized innovations, including the world's first drone-based road survey system, AI-powered document intelligence platforms, genomics pipelines improving sequencing accuracy to 99%, and AI solutions that significantly reduced operational time in maritime logistics. His work has been acknowledged by the World Economic Forum and multiple government bodies. He is also a TEDx speaker and has delivered talks at prestigious global forums, including Davos and COP28, addressing the societal impact of AI and emerging technologies. He actively advises organizations such as the World Economic Forum, Government of India, Government of Andhra Pradesh, and leading global companies including NVIDIA, Johnson & Johnson, Netexis, and Mercuria. In the field of education, Mr. Shriram has made significant contributions through initiatives such as Innovative Kids, Curl, Elevate, and Wise Up, mentoring school students and engineering graduates in advanced technologies, and helping institutions design AI and machine learning curricula as part of Board of Studies. With his rare combination of deep technical expertise, industry leadership, entrepreneurial vision, and global perspective, Mr. Shivakumar brings invaluable insights into how AI can be translated from research to impactful real-world solutions. We are truly honored to have you with us today, sir. Hand over to you, sir. Please start the session, sir. Good evening, sir.
Good evening. Good evening, everyone.
Yes.
Thanks for the introduction. This is Shivaram. So today in the talk, I'm hope everyone can hear me, right? If anyone can confirm, then it'll be good.
Yes, sir. Voice is clear.
Okay. So good. So today we are going to talk about use of generative adversarial networks in medical field. Okay. And also I requested the team here to that I'll be presenting one more presentation, because everyone is afraid of AI today, that it's going to take away jobs. I wanted to talk about the future of employment as well. Okay. I'll be talking about two things today. Okay. So one is on generative adversarial networks and how they can be used in the field of medical industry, the medical field. What are the use cases? And also on employment in the field of AI, and what are the problems and how we can overcome them. Okay, because that is one of the main things I do as part of my companies. Okay, so let me share my screen. Okay, can you see this, everyone?
Yes, sir.
Okay. So I think most of you must be knowing what generative adversarial networks are. These are models which are generative in nature. So what are generative models? Generative models are models which learn the way the data is present and generate samples similar to what they have learned. Okay. They are not reproducing. So you need to understand, they are not reproducing exactly what they have learned. It's not like memory. It's not like they are storing in a database and retrieving from the database. No, it is learning the way the data is present. Okay. So I will go slightly deeper into this. I'm not going to discuss any mathematical modeling here. I'll be talking at it at a conceptual level so that you understand it in a better way. Okay. In any generative adversarial network, by the way, this came out almost 12 years ago. Okay. In 2014 is when the paper came out, generative adversarial network paper came out. Okay. So what we do is we have two neural networks. One is a model here, if you see here, the one which I'm showing, it's called generator. The purpose of the generator is to take noise, that is, we call it as latent variable. We take noise and generate a meaningful image or meaningful content out of it. It can be image, it can be text, it can be audio, but mostly generative adversarial networks are known for images. Okay, to create an image. Now, and there is another model called discriminator. The job of the discriminator is to find whether, so it's a binary classifier. This is a fully connected network. This is a binary classifier. This is mostly CNN network, right? So this is a binary classifier. So this has to discriminator has to classify between a real image or it's a fake image. So we give two images to it. One is the image from the training set. We give that. And another image is coming from the generator. We give that. And the discriminator now has to figure out whether which one is the right image, whether the sample image coming from the data set is the original one or the one which is generated is the original one. If the discriminator is successful, because the training happens in a min-max fashion, both of them are trained at once. Okay. Now, if discriminator is correct, that means it is able to pick out which one is fake, right? Then the generator gets the weight through back propagation. You train this. If the discriminator is unable to figure out what is fake, obviously it will have the weights too. Its weights will be modified accordingly. Okay. So, and this keeps happening till when? Till the discriminator is not able to figure out which is the real image. So finally, what happens over time, the generator becomes so good at generating the images that it generates images as good as original, okay, from the data set. So the discriminator is unable to figure out the difference between the real and fake image. It stops working, basically. Its chances becomes random, 50-50. So then we stop it, and then we use this generator model. We use this for for generating new images. So the advantage here is, what is the input for this? This noise is the input for this. So by changing the noise, you can get different images. Okay. So this is the conventional generative adversarial networks. Here we can do some modifications. What we can do is, when we are passing this noise, we also can pass a text string. It can be embedded. The text string is embedded and sent into the generator while training. The text string can have image of a cat. The text will be there, image of a cat. That information is also embedded into the generator, and the generator now has to pick the cat, because in the training set also the cat is sent into the discriminator. So it is called conditional adversarial network, conditional GAN. Okay. So conditional GAN, what is the condition? The text is the additional condition. Okay. So when you actually are generating images, today they use diffusion models, but generative models are also used. Okay. So when you basically type in a text and you get an image out of it, what you are basically doing in the use case of GAN is that condition, the text is converted into embedding and passed into the generator, and the generator is basically doing the inference. Okay. So all of you must be knowing this process of this thing is called training. Once the training is over, we do inference. Inference in the sense it is used, the model is used, right? The model is there and you give a text, and based on that text, the image is generated. That part is called inference. Then this entire training will not be happening then. Okay. The training will happen, the weights will change only when it's in the training process. During the inference process, we don't do the training normally. Okay, we don't do it. We basically find out all its mistake and we say, oh, this model is not working well. Then we take it into a environment like this and train it again. Okay. So during inference, only the generator is used. Is everyone able to hear? Hello? Can someone confirm?
Yes, sir.
Okay. And you are able to see my slide also, right? Hello?
Yes, sir.
Okay, thanks. Okay. So what is happening in the training process? In the training process, what is happening is basically we are learning the data distribution. Okay, what is data distribution? You need to understand this. Okay, I've put this image, but I'll be explaining it. You need to understand it. Okay, so for every data which we are like, let's say we have taken some 10,000 images of buildings. Okay, so now this building data, by seeing the image itself, humans can recognize this is a building, this is not a building. Like that we can recognize. For models, it is not so easy because they are only seeing pixels, numbers. They are seeing numbers, right? So the way we basically understand this is mathematically. Let me tell you conceptually, right? Imagine there is a box, some black box. It has some internal structure in it. Okay, it has some internal structure. Based on the distribution of that black box, data is being generated from that black box. Okay, that generated data from the black box is only buildings. Okay, so that means the buildings, when image has a building, it has a corresponding distribution, probability distribution within that black box, which is generating that. The machine which is inside it is generating. You should imagine it that way. Okay, so imagine there is a machine which works with a certain probability distribution, and that is fitted to the model distribution, the distribution of the real world, where images, in the images, buildings are there. The building images can be generated. Okay, so it is generating that. Now your job is to train your model. Your job is to train your model to pick the to fit the independent variables within the model to generate the same distribution. Okay, so you have to generate the same. So here, if you see this is the distribution training data. So the final output data, this has to fit that distribution. Okay, so here it is not fitting. With training, it becomes closer and closer to that. Okay, so when this happens, when we give a random noise, that random noise is in a particular distribution. Probably that is in the uniform distribution, right? Because it's a random noise. So it is, all variables are uniformly distributed, right? Entropy is maximum. So when we take those random variables and we pass it through this model, the distribution changes. So the models, generative models, like for example, the previous generative model I was talking about. Okay, this here, generative model, its job is to remove the, change the distribution of the data, which is noise is uniform distribution, into the distribution of the data set. Data set distribution you should get. So here we are only finding the difference between the distributions. Okay, so here we we can use the there are various parameters to find the difference between the distribution, KL divergence and things like that. We can use that to find the difference. Okay, so that's what is essentially happening in terms of the training of the GANs. So once the GAN is trained, it can be used for various purposes. As I said, computer vision or image generation is the most important use case. Okay, generating images. It can be used for natural language processing also. It can be used for generating text. Okay, because we can use embeddings. So the text embeddings can be used, and we can make it generate language also. It can be used, one of the use cases is driverless vehicles, the autonomous cars which we drive. They have to recognize various things. But how do you generate huge amount of data for training them? So for example, today, I don't know whether you people know, 2 days back, NVIDIA released a huge monumental AI framework for autonomous driving. Okay. Before that, only 2 companies were able to do it, NVIDIA and Waymo. NVIDIA and Waymo had cars and cameras within the cars, which was collecting data. So they had huge amount of data. Using that data, they had trained the model. But NVIDIA did not have that data. So what they did, they used generative models, GANs, and earlier they were using GANs, now they are using diffusion models. They used huge amount of data generated by these models to augment by these models to train their driverless automation systems. Those are also AI, different AI models. Okay. Those models are trained by the data generated by these models. Okay. So GANs are very good at generating new data, which are similar to the distribution. Okay. So that is the advantage of it in medical use cases. Similarly, like the way we develop for driverless vehicles, various medical applications require a lot of data, and that data can also be generated using GANs. So I'll be talking about it a bit more in the coming slides. Okay. It can be used in geoscience, geo-exploration, and all those things. It can be used in data privacy by creating anonymous names and other things, because you cannot use actual data for research because it can lead to various problems. People using data thefts for scamming people and all those things. So for that reason, for data privacy also, GANs can be used. Similarly to the image generation, we can also generate audio. So today, I don't know whether you know this, you can generate music, you can generate various kinds of effects, someone touches like this, the sound which is generated, that can also be, it's a conditional GAN or a conditional diffusion model which is used, okay, to generate those things. So we can generate videos also, okay. And coming to time series is also a data which can be generated using GANs. So these are all the applications of GANs. Now, why are GANs important in 2026? Okay. So we need to know that there is a lot of data scarcity, especially for rare diseases. For rare diseases, there is not enough data. And for that purpose, GANs can be used to generate the data and use that for training the models and so on. One of the advantages of GANs is the speed of inference is faster. Training, it takes more time, but inference is much faster because it's just a generative model which is there. It's a single forward pass of the generative model, which is a neural network model, which is CNN-based neural network model. You can easily train it. Do the inference on it. Training takes time. Okay. So less images are needed for training and so on. And for privacy regulations, especially for HIPAA, GDPR, which are very, very sensitive, like you cannot store certain synthetic real information. You can use this for anonymization. You can also use this for generating similar data set. Given you have a given data set, you can create similar data set and use that for your actual research. Okay. Instead of using the real patient data, you can use fake patient data using GANs. Okay. So, and many of the things which are image based, which cost a lot of money, the cost can be reduced using GANs. I will talk about it a bit later. Okay. So because of this, there's a trend which is going on, which is people are using GANs for reducing the cost of imaging and so on. And they are also combined with diffusion models. So I've been telling about diffusion models. Let me explain a bit about diffusion models. Diffusion models are the current state of the art. SOTA, okay? Current state of the art. They are used for, when you go to ChatGPT and ask an image, or if you go to Grok or whatever, they are using diffusion models. What are diffusion models? They are also generative models. They use the physics principles of diffusion. Okay. How in the forward pass, in the training period, they learn how an image can be converted into noise. In the reverse path, that is during inference, they take noise and convert it into image. Okay, same thing, they are also learning data distribution. The methodology is different. Okay, stage by stage, a image is converted into noise. Okay, by adding more and more noise, Gaussian noise, they convert an image into noise. During that process, they learn what is happening with the image, how the image distribution is changing. Okay, that's how they learn the distribution of the data distribution of the image generation process. So in the inference, the reverse thing happens. The problem with diffusion models is it takes a lot of steps during inference also. A noise is not converted into image directly. It takes steps. So if you today generate an image in ChatGPT, it may take 40 seconds, 30 seconds, sometimes 2 minutes, because it is doing that inference multiple times. It is doing that noise reduction process. Okay, that is the reason. But GANs are faster. Okay, so computationally less expensive during inference, GANs, right? So, but the quality of GANs is much lower than diffusion models. Diffusion models give better distribution characteristics, better variety. They give better variety. GANs don't give that much variety. And the quality of diffusion models is good. So that is the reason people are using both diffusion models and GANs together. Okay. And federated learning is something which can be done through GANs, because GANs are computationally less expensive. So hence you can run it on low power devices and then combine the results and generate the output. Okay. So generative AI per se is growing in a big way in the healthcare industry. Okay. Now let us come to GANs in medical imaging. One of the things I mentioned was synthetic image generation. Okay. Synthetic image generation is basically, can you generate images similar to the ones which you have already found, so that it can be used for AI training. Some of the AI models require sometimes thousands, sometimes millions of images. If you are doing transfer learning, okay, you need less number of images. But if you are training from scratch, you need huge amount of images. Okay. So if you can create realistic synthetic image for like MRI, CT, X-ray and all those things, then it is very useful, especially for rare conditions. Rare conditions, you will not have more images. So for that, you can generate using generative AI. You cannot go and do Photoshop. It will not, at pixel level, it will not work. But if you use GANs, it will generate a very good replica. All right. And then augmented data sets can be generated for AI training, as I said, and synthetic brain MRIs and all those things we can do using this. So if you see the images here, so you can see the reconstructed image, how real they look, right? So this is actual sample of AI generated images. You can see how realistic it looks. Okay. So one more application of GANs is in denoising. Okay, you can give a noisy image and ask it to reduce the amount of noise. So let me tell you what we had done in my previous company. One of the companies I was running was into document data extraction. We had to extract information from documents and use that information for various things. Like, for example, extracting text from a contract and automatically executing the contract, things like that. Okay. So you need to understand each and every word. But if the scanning is not proper, the paper quality is not proper, then it will have a lot of noise. So this was back in 2018. We had built a GAN-based system to increase upscale the image quality of the text. and it used to work very well. So the GANs can be used for increasing the resolution of the image from the low resolution to higher resolution. Okay, so it's called super resolution. This process is called super resolution. Okay, there are other models also which can be used. We can use diffusion models as well. We can use GANs as well. GANs have been doing this, and because it requires less computational power, we can do it faster also. Okay, and then cross modality can be done. Cross modality is like, MRI is there, CT is there. Okay, they both work in a different way, right? So one gives one kind of image, other gives another kind of image. Okay. But with MRI, can you get CT? We can use AI to say from MRI generate CT. Okay, with a lot of training, the accuracy will increase. And we were speaking with the previous speaker also, we were speaking about T1, T2. T1 is like, it measures the fatness in the cells. T2 measures the water content in the cells. Okay, so in brain we have both fat and water, right? White matter and gray matter, right? So that contrast can also be got. T1, T2 contrast can also be got. Okay, with T1 you can generate T2 using AI models. Is image abnormality detection or image segmentation. A part of the image which is not proper, so which we can automatically detect. This is image segmentation problem and anomaly detection problem, which can be done through GANs. Okay, so the way it works is, you can take the image, you can chunk it up into pieces and give those, and see which one are coming from the same distribution, which one are coming from different distribution. That is one way. Or one other is, you can train your models to segment the various things, various parts of the image. Okay, that is also possible. And we can basically use that for anomaly detection. Here, till now we were talking about the generative part of the image, right? We can also use the discriminative part of the image, of the GAN model. The discriminative part of the GAN model are very good at detecting anomalies or fake images or images which are different and so on, because they are also trained during the training process. And then you have reconstruction. So what is the reconstruction? So MRI scanning it scans layer by layer, right? So to do speed up, we can increase the layer depth. Instead of doing the 1,000 layers, you can just do 500 layers. In between layers can be computed using GAN models. Okay, you can compute using GAN models, and then that can be used to create the entire MRI. So transfer knowledge is something which I already spoke about. And integration. So basically now people are integrating GAN and diffusion to get better results. One is on the speed side, other is on the training. One is good at training speed, other is good at inference speed, right? And this requires less data. Now, okay, GAN is also used in drug discovery. Okay, drug discovery is a very, very challenging task. One of the challenging tasks is basically figuring out how the drug interacts, as well as what is the structure of the drug, the 3D model of the drug. Okay, so for doing this, we can basically see, if you see the diagram here, the discriminator is getting data. Data is stored in a serialized format, in a kind of a line kind of format. From there, we have to generate a graph, and that real graph is given to the discriminator. And when we say latent space, it is basically noise. Okay, so noise generator generates some noise, and that is given to the generator. Generator also generates a graph. So now this discriminator learns the difference between this graph and that graph, like, whether they are coming from same distribution or not. And if there is something wrong, this generator is updated, else the discriminator is updated. And a new molecule which is generated in this process is if discriminator accept it, it comes and gets stored in the database as a new possible molecule. And then we can test that molecule for various things. There are other tools for testing it. So generator can be used to discover new types of molecular structures which are possible, right? And then you can see whether that structure is available, not all structures can be available in the nature. So you can check whether it is available in the, is it physically possible to have that structure and other things by passing it through other tools, the physics tools and other things. Okay. And that way you can come out with new possible molecules which can be used as drugs. So all of this is good, but this involves huge amount of process because the combination of molecules is huge. So that's where the quantum enhanced variants are coming. Quantum, you must be knowing, quantum computing is very good at doing multiple processes at once. Okay. It's like parallel processing taken it to a totally different level. Okay. All the computation happens at once, like all the parallel processing happens at once. And that's what we do. That's what we need in these kind of processes. That's where the quantum enhanced variants are becoming popular. Okay. I spoke about synthetic data and privacy. Like, for example, synthetic data are things like this: name, address, identity card, passport, driving license, car registration, and things like that, which are very specific to a person. And there is huge amount of regulation. We cannot use this actual data in the model building or training or anything of that sort. We should not use, because some part of the data can go in and sit inside the model. And if someone else is using, that information may come out, which can be very risky for the person whose data it is. So that is the reason we can use GANs for anonymization or creating anonymous data itself. Total data itself can be anonymized, not just the name and address. Everything can be anonymized. Generated, fully generated. Okay. So this is especially useful in clinical trials and especially for rare diseases where you don't have enough data. We can create the synthetic data and use it. So there are still challenges and limitations for GAN models. They are powerful. Though they are powerful, they have challenges. There is a training instability. What happens is the generator may not learn enough, or the discriminator may quickly say, "Oh, okay." The discriminator may stop learning very quickly. Then the generator is not trained properly. So these kind of training instabilities are there in this. Okay. And the output which is generated by the model may not be good enough once it is created. There can be biases also. So there are ethical considerations like biases based on the data used and so on. So there is a lot of research which needs to go on in this field to make sure that GANs are more powerful. People are now working towards diffusion models and multimodal AI, where multiple different types of data can also be used. As GANs can be used for other things, but they're very good at image part, right? But there are other models which are good at multimodal. Okay. So in terms of future directions, it is hybrid GANs model, hybrid GAN plus diffusion models, which are useful. Federated learning, which is basically using the edge devices for learning purposes and then combining all of that into one trained model. Okay. A multimodal integration for GANs like image, genomics, and text data. And explainable AI is basically using GANs for explainability and quantum GANs, okay, which can be used for massive parallel processing. Okay. So this is the end of this presentation. I will stop now to take some questions, and after that I'll go into the future of employment presentation. Okay. So if you have any questions, you can ask them directly or you can put it on the chat group.
So there is a question for
Yeah.
you, sir.
Yeah, I saw that.
Okay.
Hirul, to implement GANs, the best way is to find GitHub repos where GANs have been already implemented. You can also get collabs. It's basically in Python. Python multiple people have written GAN implementations, and nobody implements normal GAN. They build conditional GAN, and there are multiple variants of GANs also, SGAN, EN-GAN, and all those things. A lot of variants are there. So those people would have built that. You can take that, you can change the data set, and you can train it. Okay. So training GAN, for training itself, you will have one part of this thing, collab code, which will be available, and testing part as well. Okay. A quick search on Google, especially you just search GAN, GAN training, GitHub. You search this and you'll get GitHub code with all the data also, and you can use that. Okay. Any other questions on this? Okay. So let me move to the, okay, what is synthetic data? So synthetic data means, see what happens is, you have, let's say you have taken photos of cancerous cells. Okay, you have taken photos of cancerous cells. There were 80 patients, you got 80 samples. Okay, but 80 sample is not enough for you to train a AI model. You need 800 samples. How do you get 800 samples? The way you can do it is, you can take this 80 samples and show that to the GAN model, let's say generative adversarial model, and say, I want more data like this. Okay, then GAN model starts generating more and more data. So that data which is generated newly, which is not real world data, is called synthetic data. Any data which is not real world data, which is generated by a model, is called synthetic data. Is that clear? So synthetic data is used for training, but you cannot randomly put some data from Google and all those things, right? But it should look like a cancer cell. It should be very similar to cancer cell, but it is not from a real patient. It is something which is generated by computer. Okay, so that is synthetic data. So why are diffusion models better than GAN models? Okay, see, diffusion models, they do a step-by-step process. Okay, GAN works in one step. Diffusion models, they work in a step-by-step process. So what they do is, they take the noise and they basically convert the noise into image. And when they are converting in the training process, they take image, and from image they go to noise. But they don't go in one step. They take multiple steps. And in each step, they learn how the distribution is changing. According to me, because it is taking multiple steps, the diffusion model is able to learn the distribution much better than GAN models, because GAN models don't have that control. They don't have that control. It goes in one step only. Okay. Any other questions? Okay. So let me go to the future of employment post Gen AI era. Okay. So all of you know that there is huge amount of automation which is happening now. And because of that, all of us are afraid that we will lose our jobs, right? So how do we protect ourselves? How do we plan our future so that we can stay relevant and get jobs. Okay. So before that, first let us understand how AI as a field emerged. So AI is not new. AI has been there. I have been doing AI from the last 20 years. AI is famous now, correct? But it has been there for last 20 years. Sorry. I have been there for last doing this for last 20 years. And it has been there for last 80, 90 years. Okay. So the first AI started in 1940s, 50s, and it became popular. And there was a boom. In 1960s, there was a boom. So a lot of money went into it. People were expecting a lot, but it didn't turn out to be true. It was a fall. So this is called first AI winter. The second, there was another AI boom which came in, which was called expert systems. You would have heard about expert systems, fuzzy logic, and all those things, right? It came up in 80s. Okay. Then that also had a big fall. It's called second AI winter. Okay, in 80s and 90s. Okay. Somewhere in 90s, machine learning started. Machine learning is the difference between machine learning and normal AI is, see, learning is done through data directly, okay, or by human intelligence. So if it is done by data in an automated way, it's called machine learning, okay. If it is done through human intelligence embedded into a system, it's called expert systems, okay. So machine learning, because it is directly learning from data, it has a lot of power. Humans don't have to be experts. Machine will figure it out. But even machine learning, there was a lot of feature engineering going on. But when deep learning came, feature engineering was also reduced. You don't even have to do feature engineering. Everything will be done by deep learning models itself. Then came generative models. Okay. And after that, the boom started. Here, the boom actually started somewhere here. Actually, the graph is not like this. It should be like this and sudden jump here. After 2014, 2015, it went up like this. Okay. Until then, it was flat. So I used to go and try to sell AI products to various people. They used to say, oh, what is this AI? We don't know. Okay. I remember various colleges I used to go and talk about AI. Nobody knew the basics of AI also in many colleges. So this is back in 2016, I'm saying. Okay. After that, within the next 5 years, by 2020, it had become already very famous. And after Chat GPT came out with GPT-3, it became super famous. 3.5, very famous. Okay. So now we are in the third boom. Okay. Now, setting the context, AI today can write better code than humans. If you think it doesn't, please, you have to go and see what it can do. Okay. It can write better code. It can write better documents. I'm not saying it doesn't do mistakes, but a normal person, take a normal person, ask him to write one thing, and same question you ask AI, which one generates better, you see. Okay. So it can do many things better than humans. Not everything, but many things. So does Gen AI have the capability to take away jobs? Yes, many jobs it can take away. So what will happen in the future? What is the meaning of employment, and how does the job market look in the future? Okay. So it is said that 60 to 70% of the knowledge tasks now are AI assisted. AI assists in 60 to 70% of knowledge tasks, not normal tasks. Okay. A person who is using AI will surely take away a job from a person who is not using AI. If a person is not using AI, that person will lose job. Another person who is using AI will take away the job. Okay. Not only that, don't think it is only soft jobs. Even the hard jobs like the physical labor will be in trouble. Robots are coming. Okay, this is a recent news that Amazon is planning to lay off huge number of people in their factories because they are using internally multiple robots to do the tasks. Okay. And there are robots which are going to come to your house also. Okay. And 2026, 2027, these things will be commercialized and they'll be coming home. Okay. They will cost as much as a car. Okay. And they can do as much work as a maid. This is the plan. People are already working on it. Big companies have invested billions of dollars on it. Okay. So the evolution of work is going from earlier, like if you go 100 years to 200 years back, it was physical. Then it became cognitive, then creative. Now it is symbiotic. Symbiotic means you have to work with AI. AI, you should empower yourself with AI. Okay. And do a better job. It's not like you just copy paste AI. If you copy paste AI, you and the other person is same. There's no difference. You should do better than what AI is doing. So how you do it? Take what AI has done and enhance it based on your creativity. That is what is called symbiotic work. Okay, that is the future. So there are three ways of impact. One is automation, that is routine tasks being replaced. Okay, automation is already done in a massive way now. Augmentation, knowledge task enhanced. This is the current thing which is going on. In the future, autonomy, decision making by AI systems. AI will totally take all the decisions. But this future will not come so easily. Nobody will allow it, because we will not allow AI to take care of young kids, AI to do our surgeries. All those complicated tasks we will not allow. In AI in law, like making a person, punishing a person or allowing the person to go free. We cannot allow AI to do that. So there are various decision-making things where AI will not be used, but AI augmented systems will be used. Okay. So this level of autonomy, I don't think personally we will ever allow AI to do that. Okay. Always the decision-making will be with humans. Even though if AI is better than us also, final call will be taken by a human always. Okay. Now let us see what will happen to employment. There will be a lot of small companies, because earlier to start a company and run it, you needed a huge number of people. For so many people just for building the product, AI product or whatever, software product or hardware product, whatever. All of that can be replaced by machines now. Machines and agents, AI agents can do those work. So you need smaller companies. You don't need big companies. Smaller companies. But it's not like only few companies will be there. Thousands and lakhs of small companies will be there, because everyone, you can also start one company and you can also build a product. Whoever has capability who's smart, they will start their own product. They'll start their own company. They'll become famous like that. Okay. So in the future, there'll be a lot of AI-preneurs, even one-person unicorns. There is a saying that people can start, a single person can also create a $1 billion company. Okay. There is also a lot of news regarding this, excitement regarding this. And there'll be a lot of fluid roles. Roles will not be fixed. Okay. One person will be doing multiple things. Earlier, you had data engineer, database expert, then what is it called? Feature engineer. So there were roles like this earlier. I used to think, what is this in big companies especially? How can they do only one task? This is what I used to think. But now things have changed. You have to do multiple tasks, or else you'll become jobless. If you are doing only one task, AI will replace that. So you need to do multiple things. You should have a fluid roles also. In the future, some new role comes, you should learn that and do it. Okay. There will also be experts on AI. Like if you know, like AI psychologist means if you know how AI works, you can use AI to do various things in a better way than others. Okay. So that is what is AI psychologist. So they will be getting a lot of salary, because they can do something which AI cannot do and nobody else can do. So if you understand AI well, how it works, you'll be paid a lot of money. Okay. So this is something which I normally show to people. you have consumers at one end, creators at the other end. For every person, you are somewhere in between. Okay. Consumer is someone who is continuously watching TikTok or this thing, Netflix or YouTube shorts, videos, reels, shorts, and all those things. Creator is someone who is creating something new, a product, a content, or a speech. Even if you are creating a video, that is also creation. You are creating something new. Okay. If you are a creator, you are adding value. If you are a consumer, you are consuming value. Okay. Where do you stay? You should normally stay somewhere. If this is the middle, you have to stay on the other side of the middle. You cannot say, I will never consume. Obviously, you will consume something, but you should be more on the creative side. Then you will generate wealth. Okay. Generate wealth and you'll be happy also. But if you are only on the consuming side, okay, slowly you will start losing wealth. Okay. So that is what is happening in today's society. We need to see where we are. So most of the people in the future who will be only on the consumer side will suffer, and people who are on the creator side will benefit. Okay. So this all leads to human 2.0. Human 2.0 is collaboration. AI collaboration and human collaboration also. You have to collaborate with other humans. That is anyway there in our society. But along with that, now AI collaboration also comes in. Fine-tuning tools. So if two people have AI, who can do better? A person who can fine-tune AI tools in a better way, understand AI in a better way. Okay, creative synthesis, ethical reasoning. AI cannot have ethics. That's the problem. Like it will talk as if it has ethics. It can say, oh, we should not hurt. If you ask ChatGPT, can we hurt a person? It will say, no, we should not hurt, and it will give all the reason. But if you make a robot and say, go hit a boy, it will go and hit a boy. It only knows how to execute it. Okay. So we should have a system, a control over the ethical reasoning of the AI. Humans should be involved there. Okay. And humans have huge cross-domain agility. AI cannot have so much cross-domain ability. Even today, it doesn't have. Okay. We need systems thinking, higher order thinking, and so on. See, AI cannot create new innovations. Okay. Completely new innovations. So I call it as intuition. AI cannot have intuition. Humans can have intuition. That is one of the main things which humans have, which AI can never have, because AI is built using data, and data is only coming from history. So only whatever is there in history, you can take that, and if there are 2 points, in between point is not there, and you can create that in between point and say you are creative. Okay, AI is creative that way. It will find out the in between point, but it will not find a totally new point which is outside the domain, because it has never seen that data. Okay, so that is the problem with AI. Okay. So now education is going to change. Today morning, I was talking to one of the professors from IIIT Bangalore. He was telling the same thing. Nobody will care about degrees. People will only care about capabilities. Okay. So you need to learn how to learn. You need to adapt to new situation. You need to focus on skill development. You need to have non-linear and exponential learning. Non-linear learning comes when you learn many things. You are not just one expert in one, you are expert in many. And exponential learning comes when you learn things which you like. You should always do things which you like, so that you can learn faster. Okay, in that field, you will become super expert. Okay. AI and robot farms. In the future, this is one scenario, people say this. In the future, people who have a lot of money, what they will do, they will buy a lot of robots and machines, and they will make those machines work for them. And they earn a lot of money from that. I think it might happen. But one of the issue with this is what will happen to the people who didn't have money in the beginning. They will not be able to buy so many machines. How will they generate money, revenue? Okay, so that's one of the things we need to address. So that is the reason, as humanity as a whole, we need to work towards generating more jobs, so that people can get those new kinds of jobs. because old kinds of jobs will be going away, right? So we need to generate the new kinds of jobs for people. So I was talking about what AI cannot do. I already spoke about out of the box. AI cannot think out of the box, mainly because, as I told, AI is driven by data. And if it's not in the data, how will it generate new thing, completely new? Okay. It doesn't have willpower. Humans have willpower. We will say, we'll decide, oh, I have to do this, some new willpower. I have to build a big dam, and you will go and build. There are people who have, one person for 30 years, he built a road through a hill, because I don't know whether you guys know the story. A single person built an entire road inside a hill. That is sheer willpower. Okay. AI doesn't have willpower. It's a machine. Okay. We have to put willpower into it. We should say, do this, then it will do it. Okay. And then AI doesn't have intuition. Intuition is knowledge coming from outside. Suddenly it comes. Sudden click of idea you'll have, no? That is intuition. That AI doesn't have. Okay. Word knowledge. It doesn't have complete word knowledge. It has very small word knowledge. Whatever we have shown, it knows. And then it doesn't have conscience. Conscience is when you are doing something, you'll know this is bad. We should not do this. Your inside heart will say, oh, this is wrong. Okay. And you'll not do it. Nobody has told you, but still you know. Similarly, AI, can it do it? No. Unless we program or give the data, it will not know. So it will not have conscience. Okay. So AI for humanity is something which I'm working on. These are the companies I'm running. HuLearn is for education. Longer life is healthcare, to make people live longer. Here we use AI for, since it is healthcare related, let me explain a bit about longer life. We use genomic data, diagnostic data, and lifestyle data to figure out a cancer risk for different people, cancer risk, diabetes, cardiovascular, as well as dementia risk for a person. And then based on that, we recommend different food products and other things. So Innoverse Tech is into AI for building multiple AI products, which can help people. And Innoverse 360 is to bring like 6 types of growth in a person, including spiritual, physical, mental, financial, social, and intellectual growth. Okay. So in everything we use AI. So we have come out with AI products which people can use it for free and so on. Okay. So I don't have time for showing the demo, or else I would have shown demo of HuLearn. I don't have time. So you can start your own educational academy at HuLearn and use AI tools to build your content. And it uses neuroscience-based pedagogy to make learning faster and have a deeper understanding. So you can start your academy and you can start teaching people online. Okay. At the same time, longer life, as I told, genomics plus AI for longevity. Here also, I don't have time for the demo. Okay. I will end my talk with this. I will take up the questions now. Thank
Dear
you.
participants, if you have any questions, please post it in the chat box.
So yes, we can get a lot of genomics data sets. It is publicly available. NCBS website, I'll just NCBI. Okay. National Center for Biotechnology. So here you can go. I'll just put the link here. You can see this. You can get genomics data there. You can download it, use it, and all those things. Proteomics, genomics, proteomics, multiomics data you'll get there. So you're all from the same college, Srinidhi?
No, sir. Different universities, different states also.
Okay, okay.
Diverse people are there, sir.
Good to know. Good to know. Good to know. So nice talking to all of you. Why don't you, if you have any questions, you can talk to me, or you can connect to me on LinkedIn. I also give talks once in a while, so you can join there and hear my talks. Yeah. So if there are no more questions, then we can end. Or okay, yeah, there's one more question. Abdominal trauma detection and quantification of volume of destruction methods. So basically, abdominal trauma detection is based on the images from endoscopy images, basically. Is that what you are talking about? If it is endoscopy images, yes, we can actually build a AI model for this. And to get better accuracy and stuff, we can use generative adversarial networks, as I was mentioning, using CT scans. Okay. Using CT scans, once again, the same thing. You can, if you have large enough sample, you can use the same, and you have enough images, you can directly train a model. You can use image segmentation models to figure out the area, and the amount of abnormality and other things can be detected using multiple segmentation models like UNets and so on. And the amount of the damage which has happened, that can be detected by computing the area and figuring out the volume and things like that. So for that, we basically can use various approximation methods. So first is on the image segmentation side, and over that, after that, we can use other methodologies to figure out the area and the amount of problem which is there in that particular image, right? So there is one more question, sir. Can we apply augmentation technique to genomic data set also? Yes, we can add augmentation techniques for genomics data. For testing out various things, we can use it. For example, alignment. Alignment is in genomics, you have various changes which are happening. Like when you are sequencing, we don't sequence everything at once. We segment at parts, and we have to see alignment, and based on that, we have to generate a single strand of information. So for such things, we can generate augmented data for testing purposes, and we can test out whether our algorithm is working properly or not, how fast it is doing. All those things we can do. Apart from that, for directly using it, obviously not. We cannot use the augmentation techniques because it will not generate any meaningful information. But for testing purposes, we can use it. Okay. What is the scope of deep learning in MRI post-processing enhancement? As I was telling, deep learning, especially GAN models, as well as diffusion models, can be used for super resolution. Whatever MRI imaging we are getting, we can increase the resolution of it, and also for generating the missing frames. So instead of doing MRI as a 1,000-step process, we can do it with the 500-step process, as I said. In between things can be generated using the generative models. Okay. Obviously, accuracy will not be exactly same as the 1,000-step MRI, but it can get very high accuracy based on the current performance, what I've seen. Okay. So I'll just give you one example. Today, there is one big company which is using AI for email classification. Okay, they are having emails coming in. There are 160 teams to which this emails has to go. So it's a very big company. Okay, 160 teams to which the emails have to automatically be routed. Initially, they were not using Gen AI. Their accuracy was 25%. Okay. Now their accuracy is 95%. Our team built the solution for them. Okay. And the entire processing of one email happens in 3 seconds. Okay. Now they are working on how to automatically reply to those emails also. They are working on that. Okay. And we are coming out with various plans to do it. So AI is progressing at a very high speed, alarming rate. And the accuracy is also very high. I am in the industry, right? I develop solutions which go to various customers, either as services or products. So people, when they use AI products, like, they were hesitant. They were not knowing what is the accuracy. Can we use it in production? Now there are so many things in production. Already people are using in production. Okay. In industry, there's a great adoption, AI adoption, which is going on. Okay. Any other questions?
That's it, sir.
Okay. Thank you. Thank you, everyone.
Thank you. Thank you very much, sir, for the highly insightful session on generative adversarial network, GANs. Sir, your clear and intuitive explanation of GAN architectures along with use cases greatly enhanced the participants' understanding of this advanced topic. The way you bridge the theoretical concepts with the practical, some use cases and examples made the session both engaging and impactful. We truly appreciate your time, expertise, and enthusiasm in sharing your knowledge with us. The session has inspired the participants to explore GAN-based solutions in some of the applications. Once again, thank you very much, sir, for your valuable contribution to this FTP. Thank you very much, sir.
Thank you. Thank you, everyone. Have a nice day.
Thank you, sir. Participants, please stay back for the next session. Already speaker joined. We will start in 2 minutes.
Dear participants, so we'll have this assessment after this session at 6:30. So we'll have a test from 6:30 to 7:30. So after that, we'll have a valedictory session. So all the participants are requested to attend this assessment. Thank you.
Can I share the screen, madam?
Yes, sir. Good evening, sir.
Evening, madam.
Yes, sir. You can share that. Yeah, welcome back to the session 3. Good evening to all the participants. It's my privilege to introduce our session 3 speaker, Dr. M. Purnachandra Rao. He is an accomplished researcher, academician with strong expertise in cutting-edge engineering and applied sciences. He is alumni of Indian Institute of Technology, IIT Madras. With over a decade of experience, Dr. Rao has made significant contributions to teaching, mentoring, and collaborative research in his domain. After his long and impactful academic service in India, he moved to Germany to pursue postdoctoral research, further expanding his international research exposure. He is currently working as research scientist at Fraunhofer IAS Germany, a renowned global research organization. In recognition of his outstanding research contributions, Dr. Purnachandra Rao recently received the Best Paper Award from Aachen, Germany at Picture Coding Symposium PCS 2025, showcasing the international impact and excellence of his work. Dr. Purna continues to engage in advanced research, innovation, and academic collaborations, contributing to the development of next generation technologies and inspiring young researchers worldwide. Thank you for joining with us today, sir. Over to you, sir. Please begin the session.
Thank you, madam. Give me few seconds. I try to connect the.
Sure, sir.
Hello, everyone. Thank you for
Sir, slides are
join.
visible.
Okay. Thank you for joining this session. So Sujata madam asked me to go through the she has given me much lighter topic than the earlier sessions. So I will take you through the recent trends in healthcare. So the talk consists of basically we can categorize into two. The first part, like the first 5 minutes, we can spend on the recent trends in healthcare, and then the next part is the most relevant part for as an engineer, not as a physician practitioner. So the second part is more of the technological contributions part of us. So the research trends to achieve the recent trends in healthcare. So we will talk on those. What are the deep learning models they are going through? They are developing to achieve these recent trends. We will go through. So yeah. So basically, if you look at the recent trends, healthcare is changing very fast, driven by these digital tools and artificial intelligence. We are seeing more automation that reduces paperwork and speeds up routine tasks. Data is becoming easier to share safely across systems. So, and the important thing is the cyber security. So thanks to better cyber security and common standards, so care teams have a fuller picture of each patient. AI now helps with clinical decision support, flagging urgent cases, suggesting next steps, diagnosis, so predicting risks, and the recent advances in the computer vision and natural language models improves these diagnostics and turn this unstructured data into very nice documented like suppose for example radiology reports or some diagnostic predictions, and telehealth patient portals and remote monitoring makes more convenient, and precision medicine tailors treatments using genes and biomarkers and imaging. Behind the scenes, cloud and edge computing power real-time insights at a scale. So the common goal is safer, faster, and more personalized care built on strong governance and clear workflows. So basically, the medicine, the personalized medicine is taking the much attention than earlier. So earlier we have experiences with, suppose for example, blood pressure or sugar level. We have these fixed numbers. So if it is above that, then there is the patient is suffering from blood pressure or sugar. But actually, this is the scientists have realized that this is not so. We need to look through the the history of the patient, and according to that we have to decide. So this AI prediction models will take care of will consider the history of these and predict diagnose the patient's disease, not just by these numbers. So I mean these are just some. There are many trends, so I just put some trends here, and we'll look at 3-4. These are theoretical, then we'll get the models. So as if you look at the AI, so as earlier speaker also mentioned, the adoption of AI is becoming more and more rampant. So AI is moving to everyday healthcare, and 88% of health leaders expressing trust in these technologies. On the operations side, like suppose AI speeds of insurance claims and spots improper claims early and reducing the fraud. This is on the operations side. And in care delivery, next generation decision support helps with diagnosis, care planning, and risk identification. While predictive analysis forecasts the capacity, staffing, and operational risk. For diagnostics, deep learning in imaging with CNNs and transformers automates this detection, segmentation, and also classification across different segments, like for example, radiology, pathology, dermatology, etc. Reducing variation and improving throughput. And also natural language processing turns unstructured clinical notes into structured data, so enabling to generate automatic radiology reports. And personalized and precision medicine are advanced by integrating the biomarkers, imaging, and clinical data. So we use all these models and predict and suggest the personalized medicine. And this is very interesting, the trend now. And all of this must on solid foundation. So above all these, the regulatory bodies and the leadership, like clear governance, is very important for AI responsibility. So this is on the AI side. And the cybersecurity side. So healthcare is one of the most heavily targeted industries for cybercrime. So according to the EYKLAS US Healthcare Cyber Resilience Survey, 72% of healthcare executives are said to be impacted by the cybersecurity. This shows that cyber attacks are not just technical problems, they directly affect hospital operations, patients, and finances. So So to solve this, there is one important criteria called zero trust architectures. So don't believe anyone. So this is zero trust means you don't believe any system or any person. So you try to build an architecture or a system which is login through proper. So for example, there are many patients, they record their data at the hospitals, and the access to this is so is a big question actually. So this should be the data should not be shared with anyone. The patient consent must be there. So these are the recent trends. So zero trust architectures is coming up, and another major focus is the global privacy and compliance. So there are standard bodies like HIPAA in United States and GDPR in Europe, and many international laws. These rules ensure that patient data is protected and handled responsibly. So ransomware attacks also increasing. To defend against them, hospital now use network segmentation. So even though some part of the network got impacted, so this network is separated or segmented from the whole network. So these are some of the trends. And also resilient infrastructure. So healthcare systems are planning resilience infrastructure. This means ensuring that critical systems continue to function even during a cyber attack. So patient care is not interrupted. So overall, cybersecurity is now a core part of healthcare strategy, not just an IT issue. So, and then the interoperability. So if the interoperability means that different healthcare systems, software, and medical devices can share, use the patient data easily. Suppose if you go to one hospital for any checkup or any suggestion, diagnosis, so you get the data, whatever so you will go through some MRI scan, CT scan, and that recorded data will be stored in that. So now the trend is, if you go to another hospital, they will write some, okay, this prescription, go and get this data. So means, so this interoperability helps that the data should be shared and protected. The data will also be protected. So a patient hospital records, lab test results, pharmacy information can all connect smoothly without manual effort. So interoperability is becoming the backbone of the next generation healthcare systems. And so this because of all this, we'll get this interoperability, we have these benefits like better clinical decisions. So doctors can make smarter decisions because they have complete and accurate patient information, and more efficient operations. Hospitals save time and money by avoiding duplicate tests and paperwork. Finally, stronger patient engagement. Patients receive more coordinated care and can easily access their own health records. So this is another, interoperability is another aspect of recent trends. And the last one I want to mention is this digital twins. So the concept of digital twins is, suppose if a patient is undergoing some disease or some problem, so this digital twin is nothing but you give all these inputs and create a virtual model of the patient. So instead of doctors trying something on the patient directly, they simulate these health conditions, and how the patient will respond to these health conditions. They simulate on these digital twins, so that we can understand nothing will go wrong directly on the patient. So this is another recent trend of digital twins in healthcare. So basically, the data source for this digital twin simulation is this lab testing and imaging and some medical history and many variables like IoT devices now available for monitoring. So this will give the information data sources to simulate this digital twin, and then you can how these conditions will respond to the treatment we can record and then act. So the benefits are like safer and more precise care, less trial and error. So we have seen so many diseases. I mean, so these companies also are the medicine, biotechnologies. They are all like means they are they trial for some time, and for some medicines, if they have not completely trialed on different subjects, this will impact the patients in the end. So this digital twin will help. So this trial and error and early detection of complications. So these are the recent trends in the healthcare, some of these trends. So, and I will go through the research trends now. So first I'll start with the uh, actually one slide is saying, okay. So basically, I will start with the compression. So because I am working on the image compression and video compression. So the every day in an hospital, they will generate several hundreds of terabytes of data from different case studies of the patients or different diseases and different departments of the hospital. So basically, to handle this much data, we need compression. So basically, the compression uh, is nothing but everyone knows that suppose if we have an image of 256 by 256, then and also is a color image of 3 channels RGB, and each pixel will take like 3 values, and each value is suppose an integer, 8-bit integer. So we can calculate the storage of an image. So now our task is to compress this so that the data storage will be reduced. So basically, this compression is done in two most popular ways. One is directly taking RGB image as input and then given to some neural network. Mostly these models are the VAE models, variational autoencoder models. So this VAE model will create, or you have already gone through so many earlier sessions that how a deep learning network basically gives, right? So this gives a set of features. Okay, so VAE is just nothing but given a lot of data and it will compress to a low dimensional data in a like in a crude way. So this data is then entropy coding will do. So means use these probabilities like which signal is coming higher probability. Based on that, we allot the bits for each values. So these values are, it can be floating point, it can be integer. So given the input image and there is an VAE block, variational autoencoder, and then the output of this is nothing but we call it as embeddings or latents, right? So latents is nothing but these outputs, and these are given to an entropy coding, which basically compresses the information with less number of, it will basically calculate the number of the probability of each value and assign the bits for that. So then this is nothing but encoding process, and the decoding process, we give these encoded symbols and we have the inverse network. So taking these latent variables and generate the generate the image. So this is the inverse process, which is called the decoder. So basically, this is the pipeline. Given an input image, VAE, for example, autoencoder, this gives some latent variables, which is very low dimensional than the original image, like 256 by 256 by 3. Then these are entropy coded. These are sent to the decoder, and on the decoder side, these latent variables from these latent variables we want to reconstruct the image. So this is happening in the RGB space. So the input itself is RGB and the output is RGB. So this is the pipeline, and what we want to optimize this loss function for this is rate plus lambda times distortion. So sorry, actually I missed this slide. That's why I'm telling orally. So basically the rate is nothing but how many symbols this latent space is going through, that is rate, and distortion is nothing but the input image, original image, and the reconstructed image. So basically the loss function is R plus lambda D. So rate plus lambda times distortion. This is the pipeline. So this is how we do compression in RGB space. Similarly, one more most popular trend is divide, instead of doing this on RGB space, we divide this into luma and chroma, which is nothing but structure and color. So the same pipeline we apply to luma separately and chroma separately, and then in the end combine them. So that is basically compression. Yeah. So encoder decoder is nothing but it can be a so the VA variational autoencoder, which is nothing again made up of some CNN layers or some transformer layers, depending on the complexity. So in this figure, I am showing that the graph on the right side there is a graph. So basically, this graph on the x-axis, it shows that rate in BPP means, so the number of bits per pixel is mentioned on the x-axis. So 0.2, 0.4, 0.6, and on the y-axis it is PSNR. So basically, we try to, the loss function will be rate plus lambda times PSNR or MSC loss. So these are the recent rate distortion comparison. So basically, we want a curve to be, rate should be less and PSNR should be high. So for example, the purple curve, we want the so here in this case, the purple curve is the best performing method. So basically, this is the current state. There are different deep learning based models they are performing. So the biggest problem with these models are these are very, very complex. So the complexity is measured in terms of kilomax per pixel, means how many number of multiplication and addition operations are happening for computing 1 pixel. So for restoring 1 pixel. So these, if you calculate these methods, the complexity as I will show the numbers later on. These complexity numbers are very, very high. So what we tried was, so generally people try for reducing the complexity is they will change the architectural design. So what they will do is basically decoding time, we want it to be very less, because latent or the time to decode, restore the image, we want it to be very less. People want, because suppose if you are watching Netflix on your mobile in India, and the Netflix is generated in US, the content is generated in US, and so means basically we want the streaming happening. So streaming, no problem, because it has some buffer. But if there is some, suppose some video call, and I am talking here and you are listening the other side, if the restoration happens on the receiver side very late, then it will be means the latency is very high. So basically, people in architectural design, what they do, asymmetric design they do the high complexity on the encoder side and less complexity on the decoder side. This is one way of reducing the complexity. And also there are some other transformer based modelings. So this is one way of handling complexity. And the second one is overfitting the network. So this network will work only for one image. So given this input image, I will restore only that image. So there are no, so the network weights are mapped with the RGB coordinates. So there is no need to separately send the latents and all. The network weights itself act as the the network weights itself acts as the latent space. So this is one way, and then there are some pruning and quantization methodologies to reduce the complexity. So what we tried was we tried to come up with some architecture which will reduce the complexity of these coding networks. So we have come up with this architecture called tree architecture. So this is input image, and this is a simple binary tree architecture. Basically, these blue blocks are nothing but residual blocks, downsampling blocks, and these orange blocks are the upsample blocks. So this is the left side is the encoder, and the right side is the decoder, and in between there are these GEB blocks are the entropy coding. So the same thing which I have described earlier. The left side is encoder, then this Y1, Y2, Y3, Y4 are the latents, and then these are given to this entropy coder, and then the right side is the reconstructing this. So this is our model. We we have implemented this, and then so the last function we are using is r plus lambda 1 times. So we are not using distortion, only MSC distortion. We have a combination of mean square error and MSSIM distortion along with the rate. Rate means these G1, G2, G3, these symbols are Y1, Y2, Y3, Y4. After going through the entropy coding, what are the rates? What are the, like, how many bits they contribute? So basically this is the rate, and the distortion is between X and X cap. So which can be like MSC or MSSIM, or it can be LPIPS. LPIPS like learned perceptual. So basically this is another neural network based feature comparison. So it can be anything of these. So basically we want to minimize this function, and so this is what our results are. So basically the first one is the original image, and the second one is our result, and these are compared with the standard some of the standard compression models. So our model is performing better in case of colors compared to the JPEG AI is performing better in terms of structure. So basically, these are some results. You need not understand everything, but to tell that this compression, this is the pipeline basically. Encoder, latent space, entropy coding, and decoder. So so here our results are we have compared this with on different data sets, and we plotted this. So the important is this slide. So here, if you see the comparison of the complexity, so the JPEG AI is the 495 kilomax for 1 pixel, the number of operations it will take. And this TreeNet, what we propose is 60 kilomax. So, and there are still some possibilities to optimize this. Yeah, so basically, yeah, the same thing. So what we can do in the medical, like our health data sets. So the same. So last one more slide. So basically, this Y1, Y2, Y3, Y4, this encoded output. So here, if in the figure Y1, Y2, Y3, Y4, these are the different latents of the of the encoder network or some VAE model. So these outputs, if we ablation study we did, so this gives an interesting uh, feature maps. The first one looks like a low pass filtered image, and the second one is the more edges are place like high pass filter, and the third and fourth latents represents the chroma information. So we did not actually intentionally do some strategy to force the first latent to the low pass filtered and the second latent to high pass filter, but the network basically learns these latents. And if you look at the right side pictures, so this basically shows that if you use only first latent, the reconstructed image is the first one, A1, O1, and if you use the first two channels, the reconstructed image is O2. Means it's gradually, it's natural, right? Because these four latents combined together gives the output image. So what we observed was this is very nice distribution of these latent spaces. So this same model, if we want to apply for medical data, it won't work directly, because the loss function which we are using is basically perceptual loss or the pixel loss. So but in our medical image compression, we need almost lossless compression, and also even though there is a loss, the diagnostics should not be impacted by this compression. So there is a separate loss for that. People are trying. There are medical compression models like CLERC, the CLERIC, which is published in 2025. So means the pipeline, everything is same. Only thing is the loss function they optimize for the medical images, and also there will be some the network architecture also more or less same, but there will be definitely some same lines, like suppose they are using transformers, VIT transformers. So yeah, basically my point is here I want to say that this is one model or one compression model, how it will perform on the natural images, and also this model will need to be completely fine-tuned to perform on the medical image. So this information will help in the further discussions. So this is about the compression model. Now we go through the another research. So we have several research strands. So now in this presentation, I am focusing only on the foundational models. You might have heard these foundational models for image processing. Now everyone know these foundational models. You are using every day in foundational models. So we'll spend some time to understand what are these foundational models, how these are different from what I have explained in the compression model. So basically, when we talk about a foundational model, we mean a single powerful model that learns broad patterns from very large data sets and can be reused across many tasks with minimal extra training. So the compression model which I have presented is trained under like one COCO. There is one training data set called COCO data set. We have trained on the COCO data set and tested on the Kodak data set, Click data set, several 3 data sets, and mainly. So but the foundational model is different. It is a single powerful model. So that will try to basically, instead of memorizing narrow rules for one problem, it learns general purpose representations. How language is, for example, in language model, how language is structured and what visual patterns look like and how signals evolve over time. So this makes it a flexible starting point for many downstream applications. So if we have this foundation model, we can apply to many downstream tasks. So how do these models learn such broad capability is the question. So we told that this is pre-trained on very large data sets. How this can be done? How this learning can be happen through large scale pre-training. So they are exposed to massive collections of texts and images, and sometimes like, so for medical images like ECGs or waveforms. So the problem with the in the medical image, we'll discuss that. So for example, in language model, the model predicts the next token. In vision, suppose it might reconstruct. Suppose if you have given an image and you mask some portion of the image, and we ask the network to reconstruct that image. So the network learns to learn the features from these masked image and masked image patches, so that it will learn the underlying structures in these images. So basically, the self supervision or weekly supervision is very important in foundational models. Self supervision or weekly supervision means to discover structure. So we don't have labels actually. So we have, for example, in image compression, so we have we have suppose VAE models, how they train. Given input image, the output also same. So similarly, the self supervision is you have an input image and the output, you don't need any labels for that. So the self supervision is very, very important in foundational models. So the larger and more diverse the data, the more general the learned features tend to be. So this understanding is self-supervision is very important for the foundational models. So once you have this general purpose representation, then we can fine tune. So there are different ways how we can adapt to different downstream tasks, and how this can be modality agnostic. So input can be text, or it can be image, or it can be some EEG signal. So where we update, so we have the general purpose, very large pre-trained model. This we fine tune. Fine tune means we update some model slightly on smaller task specific data to get high accuracy. Prompting means we don't even fine tune. We give the right instructions. So we know this prompt engineering is one of the famous buzzwords. Like, we don't train the model GPT. We give the right instruction to get the better output. And there are like few shot learning. We give some examples. Few shot means we give, okay, it's for this input, this is the output. Like this, we give some few examples, then it will learn to generate. So these are the, so basically foundation model, you understood that it is a very large pre-trained model, and we want to learn this to represent the basic underlying structures and patterns in the images or speech. So in general AI, not medical, healthcare specific, every day we are using these foundational models like GPT, Llama. So these are the language models trained on large text corpus. They can be adapted to summarize or answer questions with minimal or additional training, or with zero shot or some right prompts. And CLIP is another language vision language model, foundation model. So these are some examples of the well-known foundation models in the general AI. And VIT, Vision Transformers, is a backbone for many image models. So it scales well with the data and is often the starting point for detection and segmentation tasks. So in healthcare, we use these ideas, but tailor them to the clinical data. So medical imaging foundation models are pre-trained on millions of X-rays, CTs, MRIs, pathology slides, often with self-supervision. So they produce embedding the transfer to many tasks, like whatever suppose if you want to do segmentation, detection, then it can be used for many downstream tasks. Clinical LLMs are basically to generate the radiology reports or any text ophthalmology reports. So there are several models, language models, vision language models in medical domain. We'll see those models, what people are trying now. So finally, multimodal medical foundation models aligns. So multimodal means it has both image and text. So suppose, for example, if you have input image and the corresponding text as the output, so this alignment enables like zero-shot classification, image text retrieval, and many more clinical applications. So basically, we'll see some examples of these medical imaging foundation models. So to clear once again, why does this matter in medicine? So traditional approaches train one model for task, pneumonia detection, tumor segmentation. For every task, there is one model. But the foundation model approach is train one base model and adapt it to many tasks. In radiology, a vision language model trained on X-ray and reports triage studies and answers questions about findings. In pathology, what a vision model can segment tumor on whole slide images. So these are for ophthalmology. There are different models for each task. So, but in benefits of this are foundational models are works well even with the limited data. So here again the concept of self-supervised learning. The biggest why these are best suitable for the medical field, because we don't have this medical data is much expensive than the general data, especially for in case of ophthalmology, it is less expensive compared to radiology and pathology. So to get this data is very, you have millions of X-ray images, but we don't have the labels, and the labeling is very expensive. So to pre-train these models with the available data by using self-supervised learning schemes, it will be perfect for a foundational model. So then once you have this model, then you can easily apply to downstream tasks. So in this, we only focus on the vision-based or language-based. So basically, vision and language both also will come for these like pathology, radiology, and ophthalmology domains. We'll see some models. What are the works recently happening? So yeah, basically this talk is about to going through what is happening. We no need to understand what this model is this. So to get an idea of what is happening in this. So basically the pipeline looks like this. Okay. So the vision pipeline foundational model, FM means foundational model pipeline looks like this. So we have vision encoders, or this encoder is nothing but basically to reduce the dimension, simple words. So input image size is down to some features. Suppose if you apply some Fourier transform or some transform like that, imagine that encoder is nothing but the output of this is nothing but some low level features or some features of this input image. Then some self-supervised learning scheme we use to learn this model to pre-train. Then once this model is pre-trained, then we can adapt to this rightmost block, adoption to the downstream task. How this can be, what are different ways we can adopt, or these are the tasks. These are the like suppose here it's mentioned full fine tuning, prompt engineering. There are different ways we can adopt. So the pipeline is this. Any foundational model, you have these encoders, then self-supervised learning, and then adoption. So the second line here, it is like, for example, multimodal components. Suppose if you have only in the first line, if you have only the input is image. For example, if you have the like some text also along with the picture, some description of the picture, that also you want to use to process, then we have the second line, which is also similar to the encoder, some auxiliary. Suppose if it is a text, it will process the text and gives the latents of the text. Okay, and then in the pre-training, so there are fusion. There is one more block called fusion. So this text we process it separately, and vision model we process it separately. Then we need to combine these two features. So there are at different stages we can combine these features. We can combine in the beginning itself, and then process use this self-supervised learning, or we can combine these features when we take decision, or at different levels we can combine basically. So these are the different fusion levels. This is the whole to pipeline any foundational model. This is the basic pipeline for uh, basic pipeline. Then here is one example. So for example, if we have some first line, it is processing the images, and it will vision encoder. Here this vision encoder, if you look at this vision encoders, here we have CNNs. So CNNs, again, there are different models, ResNet. This connext is the new recent models of the convolutions. Then there we have transformers. So these VIT and SWIN transformers are very popular in image, or it will deal with the videos. So here they selected one of those encoders. It can be VIT base, or it can be ResNet, anything. Then this generates the features. So in the self-supervised learning, there are again different schemes. Here what they use is the masked generate autoencoder. So basically what they do in this figure, they have cropped some part of the image in the input. So some parts are missing, black. Then they are using this masked autoencoder. So the output is the full image. Some parts are missing. So this will learn, the model will get pre-trained with these masked autoencoder. Or this is also called, this will come under generative self-supervised learning. Basically, this will generate the missing parts in the image. So this is one of the self-supervised learning scheme. Like there are so many schemes. So, and the last, once the model got learned completely, pre-trained, now we want to, this yellow block here is the pre-trained model, and then we want to give some extract this. Then after, so this embedding is nothing but the features whatever we got is then added to some classifier network in the end. So this will what classifier network will do, whether it is cancerous or not cancerous. So basically it will adapt to different tasks. Okay, this is one example, and second is simple, same with the text also, language also included. So this is multimodal, and here they used contrast to self-supervised learning. Contrast to self-supervised learning basically is, I will tell in further next slide. So what is the contrast to and what is generative supervised learning? And then in the end, they use it for zero-shot prompting. Means this pre-trained model, they have given this as the prompt. What does this image show? So the output is image shows liver cancer. So basically, these are different examples of the foundation models. So we can spend some time on what is this self-supervised learning. This is very important actually. So unlike supervised learning, generally in supervised learning, what we have the input images and the corresponding labels. So in self-supervised learning, this makes the foundation models practical in medicine. So we often have millions of images, but few reliable labels. So in supervised learning, we have both labels and images. So SSL basically own learning signal from inherent structure of the data. So we do this to force the model to learn useful features. It can later on reuse for diagnosis or segmentation or reporting. So broadly, SSL families, SSL in vision falls into two families. One is discriminative and generative. So again, the discriminative features, discriminative self-supervised learning can be further divided into contrastive and distillation. So discriminative self-supervised learning basically teaches the model to distinguish between samples, and generative means it try to predict the missing information. So we'll for example, the most prominent of contrastive learning is the most prominent of discriminative self-supervised learning is the contrastive learning. We suppose, for example, we take two augmented views of the same image. Okay, then suppose two crops of a, then the other one is two different crops of chest X-ray, and train the network to pull those two embeddings together while pushing apart the embeddings from, means basically what we want to say is the network to learn these two augmented views should be treated as the same, and two different parts or crops of the image should be treated as different. So this is basically the contrastive learning scheme. So they have this loss called InfoNC loss, basically information noise contrast to estimation. So like that, there are suppose for example in the figure it's shown like SIMCLR, simple framework for contrast to learning, and MOCO means momentum contrast, and swapping assignments between views. So I mean there are both. So similarly in distillation, also one of the contrastive methods, BYOL, which is nothing but bootstrap your own latent. So I mean so many are there. So what we need to choose is basically depends on the application of the uh, our task. So we need not, we need to know just these are the, so we can dig into too much, we can uh, go through the literature and see which is suitable for our task. So basically to say that there are so many ways we can learn these foundation models. Then once we have this pre-trained model, then how to generalize across wide range of downstream tasks. Suppose, for example, image classification, object detection, segmentation, like question answering. So these adoption methods are, some of the adoption methods are based on how complex we want to make, like our like how much hardware constraints we have. Suppose if you need to add some additional network and resources, hardware resources to run these models. Based on that, like it is like our call. So for example, in prompt engineering, we use the same model without changing anything. So model behavior, basically we give the right right inputs to get the like whatever the output we want. So basically we don't change the model, we give the right inputs for the, which is nothing but the prompt engineering adoption. And the second, this linear probing is this is a lightweight adoption method. So here we add some linear classifier. Okay, so we have this pre-trained model. We add this linear classifier at the end of this pre-trained model. So this is another way of like adapting to the this task. And then next, task specific heads. If linear probing, what we do, just we have added additional classifier to additional small network to the classifier to the end of the pre-trained model. But if it is not sufficient, then more powerful is task specific. In this, we add some smaller neural network modules which are fine-tuned to specific tasks. We don't change the weights of the pre-trained model is frozen. We don't change those weights. So we fine-tune the specific additional neural network module and then adapt to the downstream task. Then the next one is the parameter efficient fine tuning, which is much more so. I mean, we also allow some parts of the foundation models to change their weights. And the last one is the fine tuning. So we completely take this as the input and allow the whole foundation models and the additional network to fine tune to our task. So, I mean, basically this theory is how these foundation models we can adapt to our tasks. So this ends the foundational model, some initial introduction and understanding of the foundation models. So now we'll go through the specific foundation models for the pathology. So pathology many people already know. So pathology basically is they have one glass slide. So they take a part of or a tissue from our body and keep it on the glass slide, and they will add the chemicals, so HEM chemicals. So and then observe through the microscope and diagnose the patient. So basically this is the traditional workflow. Like with the tissue, first they prepare, and then these glass slides. Once you have these glass slides, and then we analyze this through microscope by expert lab technician and generate the report. So again, this tissue is processing also differs. And the next line, it shows the digital pathology workflow or some machine learning. For this, we use this pipeline. So the tissue preparation, so this, after getting this tissue on the glass with the appropriate liquids concentration, then they image using scanners. So these scanners, they will take different resolutions of these scans and then give to some vision models then to generate or diagnose. So the second line is the AI pipeline, and the first one is the traditional pipeline. So basically this pathology report provides the information on how the behavior of a disease. like we can have that, how they respond to therapy. So we can analyze these. So this is an example of digital pathology. So basically we have this glass slide, and this is the scanning. This is so so for us, how they capture and all, for us that doesn't matter much. But once this whole slide image, this is our input. So then our machine learning or deep learning methods vision models will come into picture. So these they will capture at different resolutions, and then our models will come into picture. So just to have the feel of what is basically the pathology. So whole slide images are very large digital pictures of tissues on glass slides. They are powerful for diagnosis and for AI, but how they look depend on every step in the lab. So the challenges here is, so every lab has the different procedures to capture these. So suppose the person who take the tissue, so the time, the cutting of the thickness of the tissue, and the uniformity of uniformity of the tissue. So because if the uniformity of the tissue changes, then if you observe through microscope, if the thickness is more, then those parts will be in focus and the rest will be defocused. So I mean, there are different challenges in handling these pathological. So here we are discussing what are all the challenges. So what are the inputs? So finally we get these pathological images. So what are the challenges in those? So, and some people, this liquid H&E hematoxylin stains they use. So basically this liquid makes these nuclei in different color, blue, purple color, and the rest of the nuclei, it convert into pink color. So depending upon the number of the concentration of this liquid also impacts the intensity or of the images. And also different scanners, basically once you have this glass slide, then different slide scanners can produce slightly different images even from the same slide. So brightness, sharpness, color balance. So how the file is compressed also matters. This will generate compressive artifacts. So these all will vary. So I mean, these are the different challenges. Yes. So to avoid this, what people you try to do is the uniform standard of operating procedures, like standard operating procedures and quality control to keep the tissue handling and staining consistent, and apply some basic color correction. So H&E slides look similar across sites. So we need to do some pre-processing basically to uniform the data, to apply some normalization. So these are the challenges. And basically these pathological images are processed in a two level. One is tile level and the second one is the whole slide image. So the pipeline we have seen already, the backbone is same, like typically like CNN architecture, like ResNet or Vision Transformer. So it takes small tiles from whole slide image and turns them into lower dimensional embeddings. Second is a task specific head or a multiple instance learning aggregator that uses these embeddings to make whole slide predictions. So basically, like we have seen whether it is cancerous or so, it will divide the whole image into tiles, process these tiles and generate the embeddings. Then in the end, use multiple instance learning, vote different votes from the different tiles and make the whole decision for the whole slide image. So yeah, alongside vision only models, vision language models also there, rapidly grown. So these systems use cross modal contrast to learning, similar to CLIP. So basically different learning. So language vision model means the self-supervised learning method also changes. Yeah, so basically we pre-train model and then same story to apply for the downstream task. So here are some of the famous models. So we need not go through all this. Just this an idea of. So basically, this table says the model name and the backbone what they are using for the prenet. Here you can see ResNet or VIT or Swin transformer, mostly ResNet and VIT, and the SSL scheme they used. The size basically says how much the training data they used to train these models. So for example, Remedis, they use 15 million tiles, which is derived from 29,000 whole slide images. They're divided into 50 million tiles, and then they trained this pre-trained model. So the source of this data is TCGA, and so whether the model is available to public or not, the last column says if it is a tick, so you can we have this model open to us. We can weights are open, so we can try inferring with some input data. So yeah, basically each role is the backbone, and the common pattern used in self-supervised pre-training, and the tiled patches, and the how many whole slide images. So basically these are some of the models. We will look to one particular model here. This is Pecan V2 model. So it's a pathological model built on vision transformer. So it learns directly from histopathology data using self-supervised learning called Dino V2. So here it's mentioned Dino V2 is distillation with no labels, is the self-supervised technique they use. So it does not need human labels basically during the pre-training. So they have the teacher-student network basically to learn these labels. And the encoder is VIT encoder. If you look at this input, the first is the whole slide image, then divided into tiles, then this given to this VIT large. VITL is the encoder. This blue lines is network they used. Then this generated these embeddings. So these embeddings, the dimension of these embeddings are 1000. So like for each tile, it will generate 1000 values. Then these 1000 values are further, we can add this downstream task. So this we can use for any like segment. We can add some classification networks in this red or orange block. Then it will the output will be cancerous or not. Or if you add some regression network, basically it will give some continuous values like how bad the degree of disease, grading the disease, right? So basically all models follow this pipeline. So for the tile based foundation models, but for whole image based foundation models, the whole image will be given. That's it, no difference. Then if whole image is given, then it is, the problem is the input dimension is very huge. So we need a lot of memory and resources to process. So it is very, very impractical. So some of the details of this model is backbone is VIT, like vision transformer large model, and the self-supervised learning is used is Dino V2, and so this scheme uses teacher-student network, and the pre-training data they used is this publicly available cancer data set with 456 million tiles. Sorry, it is not tiles, and 50,000. It is, these tiles are derived from 58,000 whole slide images. So, and the inputs are these tiles, each with 224 by 225 pixel image. So outputs are these VIT outputs, these 1000 dimensional values, then further given to like multiple instance learning head. So see the model parameters. See, very, very large model. So we cannot run on our machines like 300 million parameters. And adaptation is like we freeze this encoder and train some classifier or regression network or some segmentation depending on the task. So availability, yes, publicly available. Weights are available. We need not train the network. We can just infer. It might work with sophisticated hardware. Inference definitely might. We can try the inference of this model, giving some output, input from the data set. Yeah, so basically this to get the feel of what they are trying the foundation models. Then the next foundation models again in pathology is the vision language models. Here they use both. The input is both text and also language and also image. So the backbone is VIT vision transformer and some GPT, because language is involved. So they have this GPT also. So and the self-supervised learning scheme, same, the size of the data is 1.1 million or 208,000 the tiles they use for training, and the source of the training data and so basically these are some of the models with vision language. And the last one is the slide level model. So means here in this case we have the whole pathology slide as the input, and most of these again. So here this type specifies VM vision model or vision language model. Yeah, not much to get. So basically to have the feel that okay, this trend, the trends in medical imaging is on foundational models. Yeah, so to conclude, what are the to conclude about the pathological foundation models in pathology, there is one more model, very, very, very famous model, SAM, which is nothing but a vision model. Means the segment anything, like segment anything model. So it was trained on more than 1 billion masks from natural images and can segment objects with simple prompts. So in pathology, this SAM model directly out of box performance is limited actually. So the conclusions for pathology foundation models are: vision foundation models are driving clear improvements across tasks like tumor detection, grading cues, and segmentation, especially when trained in domain on large diverse pathology data sets. We need better data curation. So more examples of rare pathologies. So we need all varieties of pathologies. So always there is hungry for the data. So good metadata and consistent magnification standards make models more dependable. So basically tile level foundation models have most practical choice so far. They scale well. So, and the problem with the whole slide models are even the benchmarks are not available for whole slide imaging models. So that is about the pathology. So we have 15 minutes. So similarly, this I will quickly go through this. Not so I have many slides, but no means the whole idea is like even in radiology is radiology is basically the part of medicine which analyzes different kinds of these X-rays, CT scans, MRIs, ultrasound, all different multimodal data they will analyze and generate the report for the to diagnose and to generate reports. So the data sources for radiology are like plain X-rays, CT scans, and MRIs, ultrasound, and different PET scans. So X-rays and CT scans, they have produced 2D data, but there are MRIs. The other MRIs will produce the three-dimensional volumetric images. The CT scans generate volumetric images. X-rays generate 2D data. MRIs basically means uses the magnetic fields and to generate 3D images of these tissues. Yeah, basically here I have listed out what are all the data sources for radiology. So ultrasound uses very high frequency sound waves to create 3D images. It mainly used in pregnancy checkups and for cardiac assessments. Okay, so radiology reports are usually not standardized. The problem is the inconsistency in terminology and templates from one report to another. Because of this, image plus text pairing is very there is very variation. The challenge is the variation in the there is no standard in reporting. So basically is most suitable for vision language models. Radiology is. So some of the models are, so earlier radiology models are, they don't use self-supervised learning. So that's why the models are limited in their scalability. They cannot use for multiple multimodality and adaptive tasks. So some of these foundation models are these here again. So mostly radiology foundation models are vision language models. And here if you see imaging domain, here we have multimodal data. So it's not, so the input data can be X-ray or it can be CT scan. So, and the backbone again is both language models and vision transformer if it is a vision language model. Yeah, means the same self-supervised learning objective is mentioned. So these are some foundation models, especially for X-rays. These are the chest X-ray foundation models. So I think this basically the information is we can get through each models. We can look at these weights and data. So best thing is if some weights and data are available, we can go to GitHub and clone that repository and try those. Best thing instead of, so we'll get some experience with the understanding. At least first run inferring pipeline we can run and then see. Yeah, so these are the 3D models for radiology. So, and the last one, conclusions about the radiology foundation models are, So the radiology foundation models are advancing, though not as rapidly as in pathology. So much of the earlier progress has been with vision language models or with pairs of images and the text to tackle these tasks like disease classification and report generation. So basically these systems are like clip style contrast to learning, which has both vision and language models in pairs of images and the corresponding text. Early focus. So in parallel, there is a growing push for vision-only models, especially for tasks like the demand precise spatial understanding like segmentation, localization, and detection. These models avoid the challenges of building high-quality text pairs. So if only vision models, we don't need this language pairing, which are limited by sparse captions and few large report data sets. However, they face their own hurdles. Large scale 3D data sets are very rare. So 3D architectures require significant compute and fully integrated 3D models are still not widespread. So as a result, basically many solutions continue to rely on 2D slices or pre-trained networks. Even though vision language models remain indispensable when clinical text matters. So the report generation and question answering is the main report generation is the goal of these foundation models. Yeah, so like this, there are some ophthalmology, basically the study of eyes. I'll quickly go through the uh, the few points what we can have. So retinal imaging techniques like color fundus photography or OCT, optical coherence tomography. These are the advantages of ophthalmology are the we can generate the data very easily compared to the radiology and pathology, because here these data are non-invasive and less expensive than these scans of the CTs and MRI. So which makes it easier to collect the data and more suitable for AI. So the first foundation model for ophthalmology is RET-found. RET-found uses this vision transformer model. The backbone is vision transformer model, and it is trained on a very large data set over a million unlabeled retinal images. In simple terms, what can these models do? They can basically identify and quantify the eye diseases like diabetic retinopathy and age-related macular degeneration, AMD they call. So that means they just don't flag the problem. They also measure the severity of the problem. So with minimal fine tuning, we can we can apply to downstream tasks like heart failure, stroke, and Parkinson diseases also. So basically, if you see the first model RET-found, this is the first foundation model in ophthalmology. Then RET-found green came with the variant of this RET-found only. The only thing is training with so this method we can train with less data and compute resources while maintaining the comparable. So the performance is still same with less training data. Then DRET found came, then different FLAIR and DR StageNet. Yeah. So there are multi-imaging ophthalmology foundation models called Vision FM, which integrates variety of ophthalmic imaging modalities, including angiography, slit lamp, and ultrasound. So these imaging techniques can be used for visualizing other parts of the eye, not just retina, but also iris or cornea amongst, iris and cornea. So most recently, iPhone was introduced as a general ophthalmic imaging model. So so the conclusions in ophthalmology foundation models basically study progress from ret found and seeing a shift towards multimodal and multitask capability with Vision FM model and iPhone. So this handle multitask and multi inputs, multimodal inputs. So again, the benchmarking is the big challenge here. Okay, so I will the last particular case study. I will show these two specific models and close the session. The first one is the brain tumor segmentation. So basically, manual segmentation is very subjective, and automated segmentation basically assists this diagnosis. So the brain tumor segmentation model, which I am describing here, is uses this data set TCGA lower grade glioma data set sourced from Cancer Genome Atlas and the Cancer Imaging Archive. So these are the MRI scans they use as a pre-trained to train the pre-trained model, and the total number of images are 3,929 slices with this without 2,500 without tumor and 1,300 with tumor. These are collected from 110 patients with annual tumor masks. Altogether, there are about these 3,900 to 29 slices, and the input image dimensions are shown 256 by 256 with 3 channels, and the ground truth mask binary. So the output is just yes or no, like 0 or 1s, binary mask. So the data set split is training data set is 70 and 10 and 20 validation and test. So on the pre-processing steps, the first one is, as we have discussed, there are different challenges. So first, intensity standardization. So scale all MRI values in the range 0 to 1. Then the correct, so then resize all the images to 256 by 256, ensure that this, so uniformity to the CNN model. Then the output is been prepared with 0 and 1. The output mask should be with 0 and 1. So 0 is background and 1 is tumor. So this is the pre-processing of the data. So this is the model. So basically the data set, if you look at the data segmentation, the white is the tumor and the background is black. So they have used some data augmentation to improve the like variation in the data. So basically, if you have data augmentation techniques that will enhance the more generalizability of the network, and so this data processing is the cropping. Then we give this to network called UNet. So in this UNet, if you see this is UNet is very popular in vision models. If you see the marked region, that is called as encoder, basically the output of this encoder, we have very less low dimensional latent space. And the right part is the decoder. So for the encoder, they use this VGG19 so the VGG19 network. This also use this VGG19 is well known for the feature extraction. So, and there are also some skip connections. These black lines directly connected to the decoder. So these features are connected to the decoder also. So this is the network they used, and the tumor segmentation. The loss function they used was focal Tversky loss function. So this is the ground truth and this is the predicted. So they find the loss between these two using this loss function and optimize. So they use the ADAM optimizer to optimize this. So the evaluation, they have evaluated several scores like dice coefficient, AUC. AUC is to measure the separation ability between tumor and non-tumor pixel. So basically the output is pixel wise segmentation, like classification, yes or no, this pixel is tumor or not. So intersection over union is precision recall, you know these scores. So they compared this with the recent methods. The blue curve basically shows the performance of this unit-based brain tumor segmentation. So it outperforms all the measures, especially. So this is radial plot. Basically, the precision, for example, 95.4% compared to other methods. Yeah. So how they publish. And yeah, so basically we just look at one model like this. We have so several models. So whatever excites you or something interests you, and if the model is available, please go through the GitHub repository and try to run the model. So it won't execute in one step. We need to go through the install requirements, all steps we have to go through, but a good starting point. And the last model I have presented here is that, for example, for dermatology. So this basically trained data set includes like 2.1 million dermatology images collected from 11 clinical resources and institutions. So if you see this, the A part, here there are 4 types of input data. So TBP, total body picture tiles, dermatopathology tiles, clinical images. So these are 4 different kinds of inputs this model can handle. And if you see the B picture, suppose these TBP files, right? TBP tiles is 35% of data. So from where this data is coming from is represented in the B pictures. So the dark green is from HOP and MIM data set, and the rest of the 46% is from ISIC 24. So these are the data set details, and the right side, this bar plot indicates the different institutions contributed to this data set. So how many images they contributed to this whole image data set size is 2.1 million dermatology images. So this is data about the inputs or input image. Now this multimodal, if you look at the D figure, the inputs have all these 4 varieties of inputs. It can handle multimodal inputs, and the model is this PANDAM model. And second row basically represents diagnosis and lesions. So basically, after the model embeddings, if you look at the downstream tasks, this can be used for screening and diagnosis, segmentation, and longitudinal data analysis, like how these issues are changing with time. So again, for each downstream task, there is a pipeline further, and yeah, means basically this is how the foundation models work in. So if you look at the model diagram in the E figure, the same as the earlier one, the image encoder, and it will give this latent representation. Then the mask, this cross attention they have added to
Sorry
improve.
for the interruption, sir.
Yeah, done.
Participants has to attempt the test in ATAL portal. That is stipulated time 6:30 p.m. to 7:30 p.m. Sir.
Yeah,
Please.
done, madam. Last slide. The over
Okay,
done.
thank
Just yeah. So basically, these are different models. So the pink on the radial plot shows for all these like 40 tasks, this is performing well, and the numbers on the circle is like normalized to, suppose if the values are from 0 to 10, these are normalized to 0 to 100, and it shows the best perform. I mean, this model shows the best performance. Yeah, basically, I am trying to go through these example models to inspire. These are the works happening, especially related to our deep learning based research trends in healthcare, foundational models, basically. Thank you so much for your time, and that's it. Thank you for the opportunity. Thank you for all the
Thank you, sir.
participants.
Participants, if you have any questions, please put them in the chat box. Yes.
Yeah, thank you, Selakumar. Date and time were wrong. Yeah.
If you have any queries, please put them in the chat box.
Digital twin of the human heart. More input to this topic. So what basically you are working on this digital twin means, like I need more details actually. So basically for any topic, the how we train the deep learning models and adapt the data basically, but I don't know much about okay. Okay, then take care. Yeah, I will send the references. I need to look and send, means immediately not in my mind. Please get in touch with.
Okay, sir. On behalf of AICT, ATAL Academy and SNIST, we extend our sincere thanks to Dr. M. Purnachandra Rao for the insightful and thought-provoking session on research trends and case studies in healthcare using deep learning. Sir, your comprehensive overview of emerging research directions coupled with real-world case studies and practical perspectives provided valuable guidance to faculty members and researchers. The way you highlighted current challenges, opportunities, and future scope in healthcare deep learning research was extremely beneficial and inspiring. The session has significantly enriched the participants' understanding and will certainly motivate them to pursue impactful research in this domain. Once again, thank you very much, sir, for joining us.
Thank you so much, madam. Bye.
Bye, sir. Thank you, sir. Dear participants, already instructions shared. Zoom